Hello there, and welcome to The Sleepy Scholar. This evening, we will drift into the subject of one of Earth's most ancient and captivating forces, fire. It is at once a destructive power and a creative one, a gentle spark of comfort and a tempest of chemical reactions. Long before the first cities were built, before spoken language, before humanity had names for light or warmth, fire was there, whispering in the shadows and molding the trajectory of our history. It has inhabited our legends, our technologies, our cosmos, and our spirits. Fire is not an object, but a process of transformation, an active boundary separating what has been from what is to come. It shifts like an idea, devours like the passage of time, and radiates with the very same energy that fuels the stars in the heavens. The identical laws of physics that reduce a piece of wood to embers are those that power the magnificent glow of our sun. If you find solace in these tranquil explorations, I encourage you to like, subscribe, or perhaps share a comment below. It assists other quiet minds in finding this space, one sleepy traveler at a time. For this moment, simply breathe. Allow your eyelids to feel heavy and let the soft glow of the flame warm your mind. Let us start. Fire is, in essence, a chain reaction that becomes perceptible to our sight. Fire is not a static object, but a dynamic process that occurs with incredible swiftness. Molecules of a fuel source and oxygen convene, break their bonds, and then form new ones. Every single reaction liberates sufficient energy to trigger the subsequent one. This perpetual renewal is what generates the flickering light that we observe. What appears to be a stable, constant flame is, in reality, millions upon millions of chemical changes taking place in every passing moment. As molecular bonds are broken, electrons move into new configurations, letting go of thermal energy and photons, which our eyes register as a glowing radiance. The flame flickers and sways because the air around it is in constant motion, continuously changing the equilibrium of fuel, oxygen, and warmth. Too little of any single component and the reaction chain fails. Too much, and it erupts intensely before it is extinguished. The soft, wavering light of a candle wick and the overwhelming roaring front of a forest fire are both controlled by the very same chemical principles. Fire is the observable trace of matter reshaping itself, demonstrating how energy flows through the universe as pure movement. A flame is a border where chemistry transforms into light. Between the unburned air and the heated gases of combustion exists a razor-thin frontier where molecules are annihilated and reborn. Within this glowing skin, atoms reorganize at incredible speeds, exchanging bonds and emitting photons. The light itself originates from particles so minuscule that they exist for mere instants, glowing as they radiate heat and disappear. The flame's hue shifts with its temperature and with the elements it contains, painting this boundary in shades of blue, yellow, or brilliant white. The very shape of the flame shows the balance between energy and movement, where convection currents lift the hot air upward while drawing in new oxygen from below. In that slim, luminous region, matter relinquishes its stored potential energy, rendering the invisible visible. What we perceive as light is the ultimate expression of a chemical reaction reaching its conclusion. The bright skin of transformation glows in the air before it dissolves once more into darkness. Combustion is matter reorganizing itself through warmth and motion. When an object burns, it is not vanishing, but rather changing its form. The atoms of the fuel combine with oxygen atoms to create new molecules, primarily carbon dioxide and water vapor, while simultaneously releasing the energy that once held them separate. That energy radiates outward as heat, sound, and light, powering the next moment of the reaction. Each molecule that reacts passes energy to its neighbors, a microscopic relay race that persists until all available fuel has been used. What is left behind is ash, the small fraction of the material that was unable to participate in this energetic exchange. In the glow of combustion, chemistry becomes visible, revealing the hidden, restless nature of matter. The very same principles that sustain a candle flame also govern the engines that propel our world and the infernos that reshape entire landscapes. Every single burst of heat is a small act of creation, a ceaseless rearrangement of the fundamental building blocks of reality itself. The color of a flame reveals the specific elements being consumed. When a substance is set ablaze, its atoms release energy in precise quantized amounts, and those amounts dictate the color that we perceive. Sodium, for example, burns a brilliant yellow, while copper produces greens or blues, and strontium glows a deep crimson. These colors originate from electrons, which leap between energy levels and then release photons of exact wavelengths as they return to their resting state. The light spectrum from a flame serves as a unique fingerprint for the elements within it, permitting scientists to identify materials based on their colors alone. In fireworks, this chemical principle is elevated to an art form as metallic salts are meticulously selected to paint the night sky with vibrant colors. Even within a simple candle flame, a full spectrum exists. The blue area near the base indicates complete combustion, whereas the yellow glow further up is caused by carbon particles radiating heat just before they are consumed. Each distinct hue tells a story of atoms surrendering their energy, shining for a brief moment before they are changed forever. The hottest part of a candle flame is hidden just above the wick. The familiar flame of a candle appears simple, yet its heat is not distributed evenly. The area immediately above the wick, where the vaporized wax mixes with oxygen, is where it burns the hottest. In this region, temperatures can soar to over 1,000 degrees Celsius. The lower blue edge of the flame marks where the chemical reaction is most efficient, while the yellow and orange glow higher up is produced by cooler carbon particles radiating light before they fade away. The wick itself is largely unburned because the capillary action of the wax draws the flame upward, away from the fibers of the thread. If this delicate balance shifts and the oxygen flow becomes poor, the flame will flicker and produce smoke. In perfect, still conditions, it forms a stable teardrop shape, a small engine of chemistry converting wax into carbon dioxide, water vapor, and light. The warmth we feel on our skin is energy that was once trapped within molecules, now liberated to move through the air as radiant heat and light. Blue flames are nearly twice as hot as orange ones. A blue flame signifies a perfect equilibrium of fuel and oxygen, where almost all molecules are burned completely. Because no leftover carbon particles remain to glow yellow, the flame shines with a pure thermal light originating from excited molecules at extremely high temperatures. The color blue itself corresponds to higher energy photons, which means the reaction is releasing more energy with each molecular collision. Gas stoves and welding torches burn blue because their air supply is carefully regulated, producing a steady, intense heat that is ideal for cooking or joining metal. Orange flames, by contrast, are the result of incomplete combustion, where glowing particles of soot radiate light at cooler temperatures. Their beauty is found in the very visible carbon that a blue flame has already fully consumed. The difference between these two colors is a measure of efficiency and precision in the combustion process. A blue fire burns cleanly and fiercely, a sign of a balance so complete that almost nothing is left behind but heat, light, and invisible gas. Some flames can burn so cool they can be briefly touched without causing harm. Not all fires blaze with intense, damaging heat. Under specific conditions, such as when alcohol burns with a restricted oxygen supply, or when certain fuels create very weak reactions, flames can exist at surprisingly low temperatures. These cold flames glow with a faint blue light, and can remain below 200 degrees Celsius, cool enough to be touched for a split second before causing pain. The reaction in these flames proceeds slowly, releasing its energy gradually over time instead of in a single, violent burst. Scientists investigate these cool flames to better understand how combustion initiates and how to prevent dangerous explosions or engine knocking. They demonstrate that fire can exist across a vast spectrum of temperatures, from gentle, slow oxidation to the fury of plasma. Even when cool, the fundamental process remains identical: atoms exchanging energy through chemical change. These ghostly flames are a reminder that fire is not defined by its heat alone, but by transformation itself, the quiet rearrangement of matter into light. Fire can exist in almost any gas, provided the fuel and oxygen, or oxidizer, are perfectly balanced. Although oxygen is the most frequent supporter of combustion, it is not the only one. Many other gases, from fluorine to chlorine, can sustain a fire if the correct fuel is introduced. What is most important is the balance, the precise proportion of the reactants and the energy required to break their chemical bonds. Too little of the oxidizer and the flame will die as if for lack of breath. Too much, and it will consume itself in a sudden flash. In laboratory settings, scientists have successfully created flames in atmospheres of hydrogen fluoride or pure chlorine, each with its own distinct colors and behaviors. Some of these flames glow green or violet, while others are nearly invisible. These exotic fires show that combustion is a universal language of chemistry, depending only on the capacity of atoms to exchange electrons. Wherever energy can be liberated by breaking and reforming bonds, fire can potentially appear, even in environments far different from the gentle air that feeds our familiar flames. What fire consumes, it also transforms into entirely new substances. Burning is a process of creation just as much as it is one of destruction. When wood burns, its cellulose structure breaks down into gases, ash, and charcoal. The hydrocarbons within the fuel combine with oxygen to form carbon dioxide and water vapor, releasing energy as they do. The flame itself is both the cause and the visual evidence of this transformation. Every wisp of smoke carries molecules that were once part of something solid. Even the minerals left behind in the ash are rearranged remnants of the original material, altered by the heat and exposure. In this way, fire serves as a powerful agent of change, converting complex organic matter into simpler, more stable forms. Nothing truly vanishes. It simply shifts into new configurations of atoms. What was once structure becomes energy, and what was once potential energy becomes warmth and light. Through fire, matter writes new chapters of its own story in the language of chemistry. The crackle of burning wood comes from moisture flashing into steam. Inside every piece of wood, even one that feels completely dry, tiny pockets of water are hidden between the fibers. As the heat of the flame reaches these pockets, that water expands instantaneously into steam, building up pressure until it bursts violently through the wood's surface. Each pop or crackle is the sound of one of these miniature explosions. At the same time, sap and other trapped gases add their own voices to the chorus, snapping as they escape. The result is a living soundscape, a reminder that burning is not a silent transformation but a physical struggle occurring within the material itself. As the wood continues to heat, it releases volatile gases that in turn feed the flame, turning solid matter into gaseous fuel. The rhythm of the crackling logs reflects the balance between moisture, heat, and release. It is the final dialogue of a living substance returning its stored solar energy to the air as warmth, light, and sound. Sparks are tiny particles of material glowing from intense oxidation. When a spark flies from a fire or a grinding wheel, it is a tiny speck of matter heated so rapidly that it incandesces before it can vaporize. As the particle flies away from the main flame, oxygen in the surrounding air attacks its surface, creating a miniature fireball of rapid oxidation. The heat generated by this reaction is immense relative to the particle's small size, often exceeding temperatures that can melt steel. The bright trail it leaves behind is the light of atoms losing electrons and forming new oxides. In fireworks, sparks are meticulously engineered, using metals like iron, titanium, and aluminum, which are chosen specifically for their color and burn time. Even the sparks from a common campfire follow the same principle. Tiny fragments of fuel lifted into the air by rising heat, each one completing its own brief, brilliant combustion. Every spark is a microcosm of the larger flame, a self-contained burst of transformation that endures for only an instant. The shimmer visible above a flame is the air bending light as it heats up. Above every flame, the air seems to ripple like a mirage. This is because the heat rising from the combustion changes the density of the surrounding gas. As light passes through these gases of varying densities, the shift bends the light rays in unpredictable ways. Our eyes perceive this bending as a shimmer or a distortion, like looking through waves of transparent water. The hotter the air, the more significant the effect, because heat causes molecules to spread farther apart, creating layers with different refractive indices. This very same principle is what causes a road to look wet on a hot day, or makes a desert horizon appear to waver. In laboratories, scientists use laser-based techniques to study these shimmering patterns, known as schlieren, to understand how heat moves through the air. What looks like a soft halo of movement is actually a visual signature of convection. It is the visible language of air, translating invisible temperature gradients into motion and light. Flames flicker because rising air currents keep reshaping the reaction zone. A flame is not a fixed object, but a moving equilibrium between chemistry and airflow. As the hot, combusted gases rise, cooler air rushes in to fill the space they leave, feeding the fire with fresh oxygen while simultaneously disturbing its form. This action creates small pockets where the fuel-to-air ratio is constantly shifting, causing the flame to dance, pulse, and waver. Even the most subtle movement in the surrounding room alters how the heat spreads and how rapidly the molecules can collide. In perfectly still environments, such as inside a sealed chamber or in the microgravity of space, flames can hold a steady, stable shape without any flicker, revealing their true, often spherical, nature. But here in the open air, convection currents are constantly sculpting the flame, making it appear to breathe and move like a living entity. The flicker we see is the visible expression of that equilibrium being lost, tested, and re-established over and over again. It is the very heartbeat of the fire, responding endlessly to the air that surrounds it. Candlelight is formed from glowing carbon particles just before they vanish. Inside the flame of a candle, wax vapor rises from the wick and reacts with oxygen, breaking down into carbon and hydrogen atoms. The hydrogen burns cleanly and invisibly, producing heat and water vapor. But the carbon atoms linger for a moment longer, clumping together to form tiny particles known as soot. These microscopic bits of solid carbon are heated by the reaction until they glow intensely, releasing the warm yellow light we associate with candlelight. As they rise further through the flame, they are eventually consumed by the heat and oxygen, leaving behind only invisible gas and faint traces of ash. This process establishes a gradient of temperature and chemistry, from the hot, efficient blue at the base where combustion is complete, to the golden hues near the top where the particles shine brightly before they disappear. The light of a candle is not from the fire alone, but from matter poised on the very edge of vanishing. Each carbon particle glows for a fraction of a second before dissolving into the air. The flame's beauty lies in that final, transient instant of transformation. The shape of the flame is drawn by the speed and direction of the surrounding air. A flame's form is entirely dependent on how quickly the air is moving around it. In calm, still conditions, the hot gases rise directly upward, pulling in fresh air from the sides and creating the familiar teardrop shape. When the air moves faster, the flame stretches, bends, or flickers sideways, following the current. The smooth contour we see is the visible outline of convection, where warm air rises and cooler air rushes in to replace it. If the airflow becomes turbulent, the flame breaks apart into chaotic, unstable forms, twisting into waves or being torn at the edges. Engineers and scientists meticulously study these shapes to understand combustion efficiency, because every curve and flicker reveals how the heat and oxygen are interacting. In zero gravity, where hot air no longer rises, the flame becomes a perfect sphere, its shape dictated only by the slow diffusion of gases. The geometry of fire is therefore not random but is sculpted by motion. It is a constant interplay between the chemical reaction and the invisible currents of the air that give it breath. Fire can produce sound as rapid pressure waves vibrate the surrounding air. Every flame, no matter how small, generates subtle fluctuations in air pressure. When combustion happens quickly, the rapidly expanding gases create waves that move outward, which we perceive as sound. The crackle of a campfire, the roar of a furnace, and the low, steady hum of a gas flame are all different acoustic expressions of the same physical phenomenon. The specific sound depends on how fast the gases are expanding and how irregularly they are escaping. In very large fires, these vibrations can become so strong and regular that they create deep, resonant tones, sometimes called fire whirls or combustion oscillations. Scientists study these sounds to monitor the stability of engines and rockets, where flame-driven pressure waves can become powerful and dangerous. Even a quiet candle flame hums faintly, though the sound is usually too soft for human ears to detect. Fire has a voice because it physically moves the air that surrounds it, translating chemical energy into vibration, turning heat and light into a music of pressure and motion. Plasma within a flame can conduct electricity, much like a weak wire. At high enough temperatures, the atoms and molecules within a flame can become partially ionized, meaning electrons are stripped free, allowing them to move through the gas. This process creates plasma, often called the fourth state of matter, which behaves both like a fluid and an electrical conductor. Although this effect is relatively weak in an ordinary fire, it can be measured with sensitive instruments. It is possible to use electric fields to bend or stretch a flame, proving that these charged particles are indeed present within it. In plasma torches, which are used for cutting metal, or in lightning bolts, this conductivity becomes immensely powerful. In a simple candle flame, the very same principle exists, just in miniature. A quiet whisper of the same process that powers the sun. Fire, in this sense, bridges the gap between chemistry and physics, existing in a state halfway between matter and pure energy. Its plasma core can carry a current softly through the air, linking each burning molecule in a web of light, heat, and motion. Fire behaves differently in every gravity environment. Gravity is the force that shapes how hot gases move. On Earth, it pulls cool, dense air downward, while allowing lighter, hotter gases to rise, creating the familiar flickering teardrop-shaped flame. In environments with weaker gravity, such as on the surface of the Moon or Mars, this convection process slows down, and flames tend to grow wider, dimmer, and more rounded. Without strong gravity to drive the circulation of air, combustion becomes more dependent on diffusion, which is the slow, random mixing of molecules. In orbit, where weightlessness is the dominant force, flames become perfect spheres, glowing evenly in all directions with no flicker whatsoever. They tend to burn at lower temperatures but can consume fuel more efficiently because the chemical reactions are able to spread uniformly. These changes reveal just how dependent our ordinary experience of fire is on gravity's constant pull. Researchers study these space flames in spacecraft to better understand fire safety and combustion science in extreme conditions. The behavior of a flame across different gravities reminds us that even something as familiar as fire is shaped by the invisible geometry of force and flow. In zero gravity, flames become perfect spheres of light. In the total absence of gravity, the hot gases produced by combustion no longer rise, and cold, dense air does not sink to replace them. Instead, the chemical reaction spreads out equally in all directions from the fuel source, forming a luminous orb that seems to hover perfectly still in the air. These spherical flames burn very slowly, often with a dim blue color, as the process of diffusion, rather than convection, is what delivers fresh oxygen to the fuel. Because this process is so gentle and stable, the flame's chemistry becomes unusually efficient, converting nearly all of the fuel into water vapor and carbon dioxide with very little soot or wasted energy. Astronauts aboard the International Space Station have observed such flames, describing them as eerily calm like small floating stars. These perfect globes of light reveal the true, fundamental nature of fire when it is freed from the turbulence of air currents. They show us that fire is not inherently chaotic, but can be serene, quiet spheres of chemistry sustained by balance alone. Fire can continue to burn in an atmosphere of pure oxygen without any visible color. In an environment of 100% oxygen, combustion can become so complete and efficient that it may lose its visible glow. Without any unburned carbon particles or incomplete reactions to produce the familiar yellow or orange light, the process releases its energy primarily as intense heat and ultraviolet radiation, neither of which the human eye can see. The result is a nearly invisible flame that is capable of reaching extraordinary temperatures. Such conditions are incredibly dangerous because the fire becomes very difficult to detect, even as it consumes material at a rapid pace. Experiments involving oxygen-rich environments are conducted only under the strictest safety controls, since even a small spark can trigger explosive, uncontrolled reactions. This kind of colorless combustion demonstrates that light is not an essential component of fire, but rather a byproduct of its imperfection. When the chemistry proceeds flawlessly, the reaction can become silent and unseen, a pure exchange of energy that reveals how close fire can come to complete invisibility. Some metals can burn hotter than molten rock. Metals are not typically thought of as fuels, yet when they are finally divided into dust or exposed to extreme heat, many of them can ignite spectacularly. Magnesium, titanium, and aluminum all burn with brilliant white or blue flames, reaching temperatures that easily surpass the melting point of basalt or granite. Once these reactions begin, they are nearly impossible to stop with conventional methods because the metals react directly and violently with oxygen, forming extremely stable oxides and releasing enormous amounts of energy. In welding and pyrotechnics, this intensity is harnessed deliberately. But in industrial accidents, it becomes incredibly destructive, capable of melting through steel containers and concrete floors. Underwater, certain metal fires can even continue to burn, fueled by their own internal stored energy or by reacting with the water itself. These powerful flames remind us that combustion is not limited to organic materials like wood or oil, but is a universal chemical process tied to the fundamental way atoms exchange electrons. When metals burn, they reveal the raw, immense power locked deep inside matter itself. Lightning can fuse sand into glass in a single flash. When a bolt of lightning strikes sandy ground, the temperature of the bolt can exceed 30,000 degrees Celsius, which is hotter than the surface of the sun. In that fraction of a second, the grains of silica in the sand melt and fuse together, forming hollow, branching tubes of natural glass known as fulgurites. These fragile, root-like structures perfectly preserve the path of the lightning bolt as it traveled through the earth, sometimes stretching for several meters deep below the surface. Each fulgurite is unique, a frozen, delicate record of an event that lasted less than a second. Scientists study them to understand the intense electrical and thermal effects of lightning strikes, while collectors prize them for their intricate, natural beauty. The process that creates them mirrors the way humans manufacture glass, only on a far faster, more chaotic, and more violent scale. In a single brilliant flash, nature performs its own act of artistry, turning ordinary sand into a shimmering piece of glass born of fire and storm. A bolt of lightning can heat the air to 5 times the temperature of the sun. The core of a lightning strike reaches temperatures around 30,000 degrees Celsius, whereas the surface of the sun averages only about 6,000 degrees. This almost unimaginable heat occurs as a massive electrical discharge rips through the atmosphere, violently forcing electrons to tear free from their atoms. The rapid, explosive expansion of this superheated channel of air is what creates the powerful shock wave we hear as thunder. In less than a second, molecules in the air are broken apart, rearranged and scattered, leaving behind a narrow channel of plasma that glows with a brilliant white light. The surrounding air cools just as quickly, collapsing inward with a rush that deepens and extends the thunderclap. Lightning's immense power demonstrates the incredible energy that can be stored in the sky's electric fields, all of it released in a single heartbeat. Although the strike itself lasts for only a fraction of a second, its intense brightness and heat can transform everything in its path, a reminder that even the air itself can burn under the right conditions. There are flames that can burn underwater when fueled by special chemicals. Some chemical reactions are able to release enough of their own internal oxygen to sustain combustion, even when completely submerged in water. Compounds that contain chlorine or fluorine, for instance, can act as powerful oxidizers for metals like magnesium and lithium, producing intense light and heat while surrounded by liquid. These underwater flames appear almost supernatural, their light diffused through swirling clouds of bubbles. Naval engineers and scientists have studied these reactions for use in emergency flares and underwater welding or cutting torches, where the oxygen produced by the reaction itself replaces the air that the water would otherwise smother. The key lies in the chemistry, not the environment. As long as a fuel and a suitable oxidizer are present together, fire can exist anywhere. These reactions illustrate that burning is not fundamentally tied to the open atmosphere, but to the exchange of energy at an atomic level. Even beneath the surface of the sea, matter can still transform, releasing its stored energy as light that glows briefly against the dark water. White phosphorus can ignite on its own at ordinary room temperatures. Among the strangest substances known to chemistry, white phosphorus is so highly reactive that it will spontaneously burst into flame when exposed to the air. Its atoms are arranged in a strained, unstable tetrahedral structure that desperately seeks to release its tension by combining with oxygen. When that reaction begins, the material often glows faintly in the dark, a process called chemiluminescence, before igniting into a bright yellow fire, producing a dense white smoke of phosphorus pentoxide. Because it burns at relatively low temperatures and will continue to burn until it is completely consumed, white phosphorus must be stored underwater or in an inert gas to keep it from reacting with the air. It has been used historically in flares, incendiary devices, and tracer ammunition. Its extreme volatility makes it hazardous, but it demonstrates how unstable certain chemical bonds can be, showing that sometimes the mere presence of air is enough to unleash the process of combustion. Volcanoes in Indonesia burn with bright blue fire from sulfur gases. On the slopes of the Kawah Ijen volcano in Java, burning sulfuric gases release an eerie, electric blue glow that spills down the volcanic crater. These flames are invisible during the day but blaze brilliantly at night as molten sulfur ignites upon exposure to oxygen at temperatures above 360 degrees Celsius. The phenomenon looks otherworldly, like rivers of blue fire flowing alongside the molten rock. The distinct colour comes from the combustion of sulfur dioxide, a gas that burns hotter and with a different light spectrum than ordinary wood flames. Miners who work near the crater collect the solidified sulfur for industrial use, sometimes walking among these glowing blue streams. The sight demonstrates how volcanic heat can transform simple elements into vivid, haunting displays of light. This blue fire is one of Earth's most mesmerizing natural spectacles, proof that combustion can take unexpected and beautiful forms when born from the planet's molten depths. Meteor trails are miniature fires tracing through the atmosphere. When a meteoroid, a small piece of rock or metal from space, enters Earth's atmosphere, friction with the air molecules heats its surface to thousands of degrees. This intense energy causes the rock or metal to vaporize, creating a glowing trail of plasma and molten particles. The streak of light we call a shooting star is actually this brief combustion of atmospheric gases and vaporized material, lasting only a second or two before fading. Larger meteors can produce brilliant fireballs, leaving behind ionized trails that may linger for several seconds as glowing lines in the night sky. The colors of these trails can vary depending on the meteor's composition, with magnesium burning white, sodium appearing yellow, and nickel glowing green. Although most meteors disintegrate completely, some manage to survive the fiery descent to strike the ground as meteorites. The burning trail they leave behind is a reminder that even in the thin, cold upper atmosphere, fire can exist, born from the meeting of cosmic speed and earthly air. Wildfires can move faster than a sprinting human. Driven by strong winds, steep slopes, and extremely dry vegetation, wildfires can race across landscapes at astonishing speeds. Under extreme conditions, they have been recorded traveling at more than 20 kilometers per hour, fast enough to easily outrun a person on foot. The intense, radiant heat from the flames preheats the fuel far ahead of it, drying and igniting it before the fire itself even arrives. Embers carried by the wind can start new, spot fires, kilometers ahead of the main front, creating a blaze that expands uncontrollably. The deafening roar of a wildfire is the sound of millions of individual combustions merging into one vast, overwhelming reaction. Scientists study their movement using complex models and satellite data to predict their behavior and help protect communities. Despite their immense danger, wildfires also serve vital ecological roles, clearing out old, dead growth and returning essential nutrients to the soil. Their power lies in the sheer scale of chemistry unleashed across the open air, where the wind becomes both an accomplice and an architect of destruction. Fire tornadoes can rise taller than city buildings. Under precisely the right conditions, a large wildfire or industrial blaze can form a rotating column of air and flame known as a fire whirl or fire tornado. As intense heat rises rapidly, the surrounding air rushes in from all sides to replace it, spinning faster and faster as it narrows into a vortex. The result is a fiery spiral that can reach hundreds of meters in height, moving unpredictably and erratically across the ground. Inside this vortex, temperatures can exceed 1,000 degrees Celsius, and wind speeds can surpass those of many hurricanes. Fire tornadoes are rare, but they are immensely powerful and destructive, capable of lifting heavy debris and spreading burning embers far from their origin. Although they appear chaotic, they obey the same laws of physics as ordinary dust devils or whirlwinds, formed by convection and rotation, but amplified by the intense energy of the fire. When nature's air currents and fire's energy align, the atmosphere itself becomes a sculptor, shaping towering columns of flame that tower against the sky. Flames can burn sideways when driven by hurricane-force winds. In the presence of extreme wind, the familiar upright teardrop shape of a flame collapses, bending low to the ground as the air rushes past it. The sheer speed of the wind feeds oxygen to the flame faster than convection can lift the hot gases upward, forcing the flame to tilt and burn horizontally. This phenomenon can occur during intense wildfires or powerful storms when severe winds whip through dry landscapes. The flame behaves like a living ribbon, crawling rapidly across the surface rather than rising above it. Even heavy rain may not be able to stop such fires if the heat remains intense enough to evaporate the moisture instantly. Firefighters must account for this behavior when predicting a fire's spread, as horizontal flames can ignite new fuel far beyond their usual reach. The sight of a sideways burning fire is a stark capture of the raw interaction between motion and heat, showing how the elements can reshape one another under nature's most turbulent and violent conditions. Firestorms can create their own thunderclouds and lightning. In the most intense and massive wildfires, the rising column of heat and smoke forms a massive plume of air that behaves much like a volcanic eruption. As these hot gases ascend, they cool and condense moisture from the surrounding air, forming towering dense clouds known as pyrocumulonimbus clouds. Within these self-generated storm clouds, particles of ash, ice and water collide, building up an electric charge just as in ordinary thunderstorms. This can result in lightning flashing above the blaze, which sometimes ignites new fires miles away from the original firestorm. Winds swirl violently as air rushes toward the base of the storm to replace the rising column, feeding the inferno with even more oxygen. These self-sustaining systems can generate winds stronger than hurricanes and temperatures that rival volcanoes. Entirely new weather patterns emerge from the fire's own energy, creating rain, hail, and lightning, all born from the combustion on the ground. A firestorm is not just an environmental event, it becomes an atmospheric engine, capable of shaping the weather above it through the sheer power of heat rising into the sky. The hottest flames on Earth can exceed 3,000 degrees Celsius. Under controlled, artificial conditions, flames can reach astonishing temperatures far beyond what most natural fires are able to achieve. Acetylene torches, for instance, can burn hotter than 3,000 degrees Celsius when mixed with pure oxygen, which is hot enough to melt steel and even vaporize glass. Some chemical reactions, such as the burning of magnesium or thermite mixtures of aluminum and iron oxide, produce even more intense heat, glowing with a brilliant white light as they tear through solid metal. These extreme flames are used in welding, cutting, and specialized industrial manufacturing processes where precision and power demand temperatures higher than any volcano. At such intense heat, matter becomes a fluid of electrons and ions, a plasma radiating energy across the entire visible spectrum. The air around such a flame shimmers violently as molecules are torn apart by the heat. While incredibly dangerous, these controlled fires reveal the outer limits of combustion chemistry, where the boundary between a simple flame and a true plasma begins to blur into pure brilliance. Some laboratory plasmas can reach heat greater than the center of the sun. Inside highly specialized research facilities, scientists are able to create controlled bursts of plasma that reach temperatures in the millions of degrees. In fusion experiments, powerful magnetic fields are used to confine hydrogen atoms so tightly that they overcome their natural repulsion and fuse into helium, releasing a tremendous amount of energy as heat and light. For brief, fleeting moments, these artificial suns can burn hotter than the core of any star. The plasma itself glows in vivid blues and purples as electrons move freely through the superheated, charged gas. Despite the astronomical temperature, the total energy is contained within a very small volume, making it safe for study within its containment vessel. Such experiments are exploring the very same forces that power the entire cosmos and could, one day, provide a source of limitless, clean energy. The heat and light inside these chambers are reminders that fire, in its most extreme form, becomes indistinguishable from the light of a star. At those temperatures, matter behaves like pure energy, echoing the conditions that existed in the first moments of the universe. Fire can melt stone and leave behind glassy black surfaces. In nature, extreme heat can transform solid rock into liquid glass. When lava flows over sand or stone, or when a powerful lightning bolt strikes the ground, the intense temperature melts the minerals and fuses them together, forming smooth, shiny layers. This process, known as vitrification, often locks bubbles of gas and streaks of ash inside the glassy surface as it cools. Ancient hill forts in Scotland and Ireland show evidence of walls that are being melted together, a sign of fires hot enough to fuse solid rock, whether during a battle, a ritual, or by accident. In laboratory furnaces, similar effects can be reproduced at temperatures above 1000 degrees Celsius. The resulting black, glossy glass holds the memory of the fire's passage, frozen in solid form. Each piece of vitrified rock tells a story of transformation, of solid matter briefly becoming liquid under heat so intense that it permanently changes the landscape itself. Fire's ability to melt stone shows that even Earth's hardest materials can yield and transform when touched by sufficient heat. Molten metal fires are almost impossible to extinguish with water. When metals such as magnesium, sodium, or aluminum ignite, they burn with a ferocious heat and react violently and dangerously with water. Instead of cooling the fire, the intense heat causes the water, H2O, to split into hydrogen gas, H2H and oxygen, O, which provides fresh fuel and oxidizer to the fire, feeding it further. The result is often an explosive reaction that can hurl molten metal droplets across a wide area. Firefighters must use special Class D dry powders, such as graphite, copper powder, or sodium chloride, salt, to smother these blazes. These powders work by cutting off the oxygen supply and absorbing the intense heat. In industrial settings, molten metal fires are among the most feared because they can easily melt through steel floors and machinery. Even concrete can crack and vaporize when struck by such intense heat. These reactions demonstrate that fire is not merely a surface phenomenon, but a deep chemical process that fundamentally reshapes materials at the atomic level. In the wrong conditions, water becomes an accomplice to the fire, releasing new energy into the very flames it was meant to stop. Aluminum dust can ignite explosively when dispersed in the air. Finely powdered aluminum, when suspended in the air, forms an invisible cloud of potent fuel just waiting for an ignition source. Each microscopic particle has a vast surface area exposed to the surrounding oxygen, allowing combustion to happen almost instantaneously once it is ignited. The reaction releases an immense amount of energy, producing powerful shock waves and intense, brilliant heat. This phenomenon is known as a dust explosion, and it can occur not only with metals, but also with many organic materials such as flour, sugar, or coal dust. Factories that handle fine powders must install special ventilation and electrical grounding systems to prevent static discharges that could trigger such a devastating event. In aluminum processing plants, a single electrical spark from static electricity or friction can be enough to unleash an explosion powerful enough to destroy an entire building. The danger lies in the combination of chemistry and geometry, where tiny, seemingly inert particles can turn the air itself into a volatile fuel. In that moment, the boundary between a solid and a flame disappears completely. Gasoline vapors can ignite from static electricity alone. Liquid gasoline itself does not actually burn. It must first evaporate, releasing a cloud of flammable vapor. When that vapor mixes with the air in just the right proportion, even a very small spark can cause a dangerous ignition. Static electricity from sliding across a car seat, from clothing, or even from the movement of the gas nozzle itself, can be enough to trigger a flash fire. This is why fuel stations use grounding systems, conductive hoses, and strict safety instructions to prevent any possible ignition sources. The amount of energy required to start the reaction is minuscule, yet the result can be devastating. The flame front travels almost instantly through the vapor cloud, returning to the liquid surface and setting the entire container ablaze. Once it is burning, gasoline produces immense heat, feeding itself through rapid, continuous evaporation. The lesson from this chemistry is that the danger often hides in what is invisible. A fire can begin not from a large, open flame, but from the smallest, unseen spark where energy and vapor meet for a single instant. Even snow can burn if mixed with the right chemicals. Under precisely the right chemical conditions, fire can exist even within frozen landscapes. Certain highly reactive alkali metals, such as sodium or potassium, react violently with water by tearing apart the H2O molecules, releasing hydrogen gas and a great deal of heat, an exothermic reaction. When these elements come into contact with snow or ice, the reaction can generate enough immediate heat to ignite the hydrogen gas it just created, creating flames that seem to burst directly from the frozen surface. This paradoxical and startling sight defies our instincts, yet it follows simple, predictable chemical laws. The same reactions are often used in controlled laboratory experiments to teach students how exothermic processes work. These burning snow reactions reveal that fire does not depend on a hot environment to begin, but only on the potential energy stored within chemical bonds. When those bonds break and recombine to form more stable ones, heat and light will appear, regardless of the surrounding temperature. Even in the coldest environment, the laws of energy remain unchanged, allowing a flame to bloom where ice should rule. Flames can appear green when copper is part of the fuel. When copper, or its various salts, are introduced into a flame, their electrons absorb energy from the heat and jump to higher, excited energy levels. As they immediately fall back to their original state, they release that excess energy as photons of light in the green part of the spectrum. This process creates a vivid, emerald green glow that stands out dramatically against the warmer yellow and orange hues of most common fires. This effect is most familiar in fireworks displays, where compounds like copper chloride or copper acetate are used to produce bright green bursts of light. In laboratories, similar colors appear when copper compounds are heated in a flame for chemical analysis in what is known as a flame test. The exact shade of green can depend on the specific compound used and the temperature of the flame. Even trace amounts of copper can tint a fire, revealing its chemical fingerprint. This phenomenon demonstrates the intimate connection between light and matter, where the atomic structure of an element dictates the color it produces. Each green flame is a brief glimpse into the quantum behavior of elements, showing how invisible atomic energy becomes visible as beauty. Certain alcohol fires are invisible in daylight. Some types of alcohol, such as methanol or pure ethanol, can burn so cleanly that the flame produces very little soot and, consequently, very little visible light. In bright sunlight, these fires can be nearly impossible to see, even though they are still releasing intense heat. The chemical reaction between the alcohol vapor and oxygen creates mostly carbon dioxide and water, leaving no glowing carbon particles behind to color the flame yellow or orange. This unique property makes alcohol-based fuels both useful and dangerous, particularly in laboratories or in professional auto racing, where an accidental ignition may go unnoticed until it is too late. An invisible flame can typically be detected only by the heat it radiates or by its very faint blue glow in dim lighting conditions. Firefighters and chemical safety specialists often use thermal imaging cameras or ultraviolet sensors to identify and locate these hidden fires. The very purity of the combustion makes them ghost-like, a reminder that not all flames announce their presence with bright light. Sometimes the most complete and efficient fires are the hardest ones to see. The first wildfires began before trees evolved. Long before vast forests covered the continents, lightning strikes would set fire to primitive land plants and dry mats of algae. These very early wildfires consumed small, low-lying vegetation and released gases into the atmosphere, influencing the delicate balance of oxygen and carbon dioxide. Geologists have discovered fossilized charcoal dating back nearly 500 million years, preserving the physical evidence of those ancient burns. The later arrival of trees, which provided a much denser and larger fuel source, intensified the fire cycle, especially as oxygen levels in the atmosphere rose high enough to sustain massive, long-lasting fires. Wildfire thus predates the existence of forests, and even the complex ecosystems that now depend on them. It has always been a part of Earth's natural rhythm, shaping the course of evolution by selecting for species that could either resist or recover from the passage of a flame. In those early ancient ages, fire began its dual role as both a destroyer and a creator, helping to sculpt the very landscapes where complex life would later flourish. Lightning was Earth's earliest natural ignition source. Before humanity learned to create sparks at will, lightning was the only force on the planet capable of setting the world aflame. Each bolt carried millions of volts of electricity, striking trees, dry grasslands, and deep peat bogs. The resulting fires transformed entire landscapes, releasing trapped nutrients from dead matter and clearing space for new growth to begin. Animals learned to flee or adapt, and plants evolved specific traits that allowed them to survive, or even depend on, periodic burning for their life cycle. The ancient atmosphere was often rich in oxygen and reactive gases, making ignition by lightning a frequent and widespread event. Some scientists theorize that these natural fires helped to shape the planet's early chemistry, producing complex compounds in the smoke that may have later contributed to the development of life. Every time lightning flashes today, it recreates the same ancient, powerful process that first connected the sky and the earth through flame. It remains a living reminder of nature's power to spark transformation, bridging the raw energy of the heavens with the matter of the world below. Humans learned to keep embers alive long before they learned to spark new ones. Early humans discovered that fire could be captured and preserved even when they did not possess the knowledge or tools to create it from scratch. By carefully covering glowing embers with ash to restrict oxygen, or by carrying smouldering sticks and fungi from one camp to another, they could keep a source of heat alive for days or even weeks. These traveling fires provided essential warmth, protection from predators, and the crucial ability to cook food. Archaeological evidence shows ancient hearths where coals were clearly maintained over long periods, indicating that firekeeping was a vital survival skill. It was only much later in human history that our ancestors learned to reliably strike sparks from stones like flint and pyrite, or to create friction fires with wooden tools. The ability to keep embers alive bridged the critical gap between the discovery of fire and the mastery of it, allowing early human societies to migrate, survive, and thrive in new, colder environments. Each preserved ember was a small, precious seed of civilization, a captured piece of the wild world's energy, carried carefully into the unknown. Charred bones found in ancient caves show that early people cooked with fire almost 2 million years ago. Archaeological sites in Africa have revealed blackened animal bones and distinct ash layers dating back nearly 2 million years. This is powerful evidence that early hominids like Homo erectus not only used fire, but also understood its transformative potential. Cooking food softened tough meat, made fibrous plants easier to digest, and unlocked vital nutrients that could not be accessed from raw food. Many anthropologists believe this dietary shift was a crucial turning point, supporting the growth of larger, more energy-intensive brains and changing the course of human evolution forever. The traces of fire left behind in these ancient caves show deliberate and repeated use, rather than just an accidental or opportunistic burning, with repeated heating in the same locations. These hearths mark some of the earliest steps toward technology and culture. Fire ceased to be just a threat and became a tool. It became a companion that shaped human destiny. The glow of those early distant flames still burns symbolically in every meal we cook, every lamp we light, and every home we warm. Firelight extended human activity far beyond the daylight hours. For most of prehistory, nightfall meant the end of activity. It meant darkness, danger, and rest. Fire changed that forever. With a reliable source of light, people could gather together, cook, craft tools, and share stories long after the sun had set. The flickering glow of torches and campfires created new social spaces where communities could form and culture could grow. Shadows moved like living shapes across the walls of caves and shelters, perhaps inspiring imagination, ritual, and the first forms of art. The warmth of the flame also kept predators at bay and provided a shield of safety in the vast wilderness. Over countless generations, firelight became a powerful symbol of knowledge, spirit, and awareness, a beacon of human consciousness in a vast world of night. It transformed our relationship with time itself by extending the day, allowing for thought, creativity, and social bonding to continue beyond nature's rigid rhythm. Every spark of human progress and culture arguably began in those shared hours when darkness met flame, and minds first learned to think and dream by its gentle glow. Campfires were once the only protection against nocturnal predators. In the ancient wilderness, the small circle of light cast by a campfire marked the absolute edge of safety. The scent of wood smoke and the sharp crackle of the flames kept most animals wary, while the radiant heat discouraged insects and the biting cold. Early humans would gather close to these small, flickering barriers of light, resting with the knowledge that few creatures would dare to cross into the glow. Fossilized hearths discovered near ancient campsites show how groups strategically used fire not just for warmth or cooking, but as a crucial form of defense. Even large, dangerous predators like lions and hyenas learned to avoid the unfamiliar, moving light of open flames. The campfire became a fortress of flickering motion, a living guardian that never slept. Within its small, warm radius, humanity began to feel secure, inventing tools, stories, and songs. Fire did not just protect human life. It provided the secure space needed for reflection and cooperation, the very things that would eventually shape the course of civilization itself. Ancient storytellers may have invented language around shared firelight. For countless generations, human families and tribes gathered at night to share warmth, food, and tales. The hypnotic, steady rhythm of the flames may have given a rhythm to their words, and their gestures would have mirrored the dance of the light and shadows. Anthropologists and linguists have theorized that the campfire's intimate circle may have been the very first classroom, the place where elders passed knowledge, history, and survival skills to the next generation through spoken story. In that protective glow, early language could evolve from simple sounds and gestures into complex meaning, allowing for sophisticated communication to take shape. The interplay of the human voice, the moving shadows, and shared emotion turned the firelight into a stage for the imagination. Every word, every myth, and every lesson told by the light of the flame was carried forward through time, shaping culture and collective memory. Around those ancient fires, humanity learned not just to speak, but to dream together as one. The bond between storytelling and fire remains deep within us, echoing through every spark of creativity that still lights the darkness today. Early humans discovered that certain stones could strike sparks when hit together. The discovery of spark-making stones, or percussion fire, was one of the great turning points in human history. When a hard stone like flint or chert was struck against an iron-rich mineral like pyrite or marcasite, tiny fragments of the iron-rich stone would fly off, glowing with intense heat from the friction. Those tiny hot sparks could then be caught in dry grass, moss, or fungus, creating a new fire on demand. Mastering this technique freed people from their dependency on finding natural flames, like from a lightning strike, and from the difficult task of keeping embers alive, allowing them to make fire whenever and wherever they needed it. Archaeological evidence of specialized flint, strikerlite, tools shows that ancient humans carried these specific stones with them for this exact purpose. The rhythm of striking the stones and catching the spark became a vital ritual of survival. Each successful attempt marked the triumph of knowledge and preparation over chance. With every new flame they created, humanity gained more control over energy, transforming a wild danger into a reliable utility. The spark between those stones was more than just fire. It was the first expression of human ingenuity, the moment when intelligence met the fundamental physics of the earth. The mastery of fire reshaped human evolution by allowing for cooked food and warmth. Cooking changed everything for our ancestors. By breaking down tough proteins and complex starches with heat, food became far easier to chew and digest. This freed up immense amounts of metabolic energy that was once spent on processing raw sustenance, which in turn could support the development of larger brains and greater physical endurance. The reliable warmth from a controlled flame allowed humans to migrate into much colder climates, dramatically expanding the human presence across the entire planet. Fire also served to sterilize water and food, reducing the incidence of disease and improving overall health. Over many generations, this new tool shaped our anatomy, our behavior, and our culture. Social life began to form naturally around the shared hearth, where cooperation and sharing replaced individual competition. The mastery of the flame thus marks the boundary between animal instinct and human civilization. In its light, humans became the creators of their own environment, no longer bound strictly by the natural rhythms of the sun and the seasons. The story of human evolution is incomplete without fire, the constant companion that carried humanity from the wild into the warmth of its own making. Some early cultures believed that every flame held a spirit. In the earliest myths and belief systems, fire was often seen as a living being, an entity that breathed, moved, and acted with its own independent will. People believed that each flame contained a consciousness or a divine essence that connected the human world to the sacred spiritual realm. Ritual fires were tended with great care and profound respect, and they were fed with special offerings of food, precious oils, or incense. Many ancient traditions saw the flame as a messenger, a conduit that carried prayers and offerings upward to the gods in its rising smoke. In temples and on home hearths, the fire was both a practical tool and a divine presence, symbolizing purity, transformation, and constant renewal. The way it consumed material yet created light and heat inspired both awe and reverence. Even today, the simple act of lighting a candle for a ritual or remembrance preserves a fragment of that ancient belief in the flame as a living spirit. Across countless cultures and spanning all of time, the fire's glow continues to represent life itself, a powerful reminder that energy, warmth, and the soul are all intertwined in the endless dance of light. Ritual fires were used to mark the changing seasons and important celestial events. Across the ancient world, the rhythm of time was kept not only by observing the stars and the sun, but by the lighting of ceremonial fires. Great bonfires and torches were lit at solstices, harvest festivals, and equinoxes to honor the turning of the heavens. These ceremonies carried deep communal meaning, connecting earthly life with the grand, predictable cycles above. In many cultures, the flame represented renewal and hope. Its light mirrored the symbolic rebirth of the sun after the winter solstice, or the return of fertility to the land in spring. Priests, shamans, and villagers would gather in circles of heat and shifting shadow, watching the sparks rise like prayers into the vast night sky. Fire became the medium between heaven and earth, a visible, pulsing heartbeat of the cosmos. Its glow measured both the passage of time and the process of transformation, reminding humanity that our existence follows the same essential path as a burning log: ignition, a period of brilliance, and a slow, eventual fading into embers. Through ritual fire, the universe was celebrated as something living, cyclical, and divine. Charcoal was the first engineered fuel created by humans. Long before coal or oil were harnessed, ancient people discovered that burning wood slowly, without sufficient air, produced a lighter, cleaner, and more efficient fuel. By covering a pile of wood with clay or soil and allowing it to smolder for days, they created charcoal, a black, porous material that burned much hotter, cleaner, and longer than the original wood it came from. This breakthrough completely revolutionized the use of fire. Charcoal allowed for the high temperatures necessary to smelt metals like copper and tin, and to fire durable ceramics in kilns. It powered the first forges, kilns, and eventually entire ancient economies. Archaeological sites show evidence of charcoal pits dating back tens of thousands of years, clear proof of a deliberate and sophisticated control over a chemical process. Unlike raw wood, charcoal could be stored indefinitely without rotting and was much lighter to transport. Charcoal marked humanity's first significant step toward manipulating matter on purpose, transforming a simple, natural flame into a precisely engineered industrial tool. It was the crucial bridge between the natural world and the artificial one, the place where human intention met the hidden science of heat and transformation. The control of fire enabled the first permanent settlements in cold regions. Before the mastery of heat, human migration was largely limited to the world's warmer, more temperate climates. Fire changed that limitation entirely. With the reliable ability to create and sustain warmth, people could suddenly survive harsh winters, preserve food by drying it, and build permanent shelters. In regions that were previously uninhabitable, the hearth became the absolute center of early homes, and the first villages grew around these dependable sources of life, giving heat. The stability provided by fire meant that families could remain in one location through all the seasons, allowing them to cultivate land and domesticate animals. Archaeologists consistently find ancient, dedicated hearthstones in the remains of the oldest dwellings across Europe and Asia, tangible proof that the flame was the foundation of permanent settlement. Beyond mere survival, fire brought comfort, light, and safety from predators. It allowed humans to take the cold, dark wilderness and turn it into a livable space, a home. The steady glow inside those first huts and caves marked the true beginning of civilization's expansion into the wider, colder world. Pottery was invented when clay accidentally hardened near a fire. The story of pottery, one of humanity's oldest technologies, likely began with a simple accident. A piece of wet clay, perhaps from a basket lined with it, was left too close to a hearth. It cracked, darkened, and then hardened into a new and surprisingly durable material. People soon realized that this heat-transformed earth could be intentionally shaped into vessels that held water, food, and grain without leaking or dissolving. This profound discovery changed the fundamentals of daily life. Pottery made long-term food storage possible and made cooking much more efficient, allowing communities to settle down, store surpluses, and grow in population. Over time, the firing techniques became more sophisticated, evolving from simple open-pit fires to enclosed kilns that were capable of reaching much higher, more consistent temperatures. Decoration naturally followed utility, with painted and carved designs turning these functional containers into works of art, and cultural expression. Every single ceramic shard unearthed by archaeologists today carries the symbolic fingerprints of that first ancient revelation that fire could not only destroy, but could also create. Pottery stands as one of humanity's earliest and most important technologies, born from keen observation and fortunate chance. A perfect, transformative meeting of earth, water, and flame. Metalwork began when people noticed shiny beads forming in campfire ashes. The very first use of metal may have been discovered by complete accident. When ancient fires were built over certain types of rocks or mineral ores, the intense heat of the charcoal embers sometimes caused molten droplets of metals like copper or lead to appear among the ashes. Early humans, naturally drawn to their brightness and strange properties, likely began experimenting with these shiny materials, slowly learning that heat could be used to extract them from the stone. This simple curiosity gave birth to the entire field of smelting and the new age of metallurgy. By building hotter and hotter fires, using charcoal for fuel and air bellows to increase the temperature, people learned to transform raw, dull ore into gleaming metal for tools, ornaments, and eventually weapons. Metal reshaped human society, gradually replacing stone with its superior strength, durability, and flexibility. The spark of wonder that led an ancient person to collect those first few glimmers of metal from the coals opened the path that leads directly to our modern technological world. Each tiny, shiny bead found in the embers of an ancient hearth was a small revolution, proof that fire could reach deep into the earth itself and bring out its hidden treasures. Ancient glass was discovered when sand fused in extreme heat. According to a legend told by the Roman historian Pliny, ancient Phoenician merchants discovered glass when they were cooking over a sandy beach. They supposedly used blocks of mineral soda, natron, from their cargo to prop up their cooking pots. The legend states that the intense heat of their fire melted the blocks of soda and the beach sand together into a translucent, liquid sheet, revealing a new substance unlike any other. Whether this story is myth or truth, early glass first appeared in regions where fire, sand, silica, and a flux like plant ash or soda met in the right combination. Natural glass also formed from lightning strikes, fulgurites, and volcanic flows, obsidian, likely inspiring human imitation. Once humans learned to recreate this process deliberately in furnaces, glass became one of civilization's most defining and beautiful materials. It allowed light to pass through a solid barrier while protecting from the elements, turning fire's destructive heat into an act of creation and clarity. Ancient glassmakers were often revered as alchemists or magicians, masters who could turn common earth into transparent light. Every window, lens, and vessel we use today owes its existence to that first transformative moment when someone looked into the pooling, molten sand and saw the miracle of melted light. The first torches were likely resin-soaked sticks from pine trees. Before the invention of oil lamps or candles, humans lit their nights with the simplest of tools, torches. Sticks of wood coated in the resin-rich sap from pine or birch trees would burn with a bright, steady, and long-lasting light, allowing the flame to be carried from one place to another. These handheld fires illuminated deep caves, guided nocturnal hunts, and marked safe paths through dark forests. The sticky resin acted as both a potent fuel and a glue, holding the ember to the wood and making the flame more resistant to being extinguished by wind or rain. Some of the oldest and most famous cave paintings in the world show soot marks and discarded torch ends along the walls, physical evidence of the torchlight that guided the ancient artists as they worked deep within the earth. Over time, torches also became powerful symbols of ceremony, knowledge, and truth, carried in rituals and processions. Their steady flame came to represent the continuity of light in an ocean of darkness. Each torch was both a simple tool and a profound symbol, a portable, personal sun that allowed humanity to explore, create, and connect beneath the vast, dark canopy of the prehistoric world. Early lamps burned animal fat and glowed with a smoky light. Long before the invention of candles, people created light using shallow bowls carved from stone, which they filled with melted animal fat, tallow, or fish oil. A simple strip of plant fiber, such as moss or twisted reeds, served as a wick, drawing the liquid fuel upward through capillary action to where it could be burned, producing a dim but remarkably enduring flame. These primitive lamps illuminated the earliest permanent homes, dark caves, and sacred shrines. The smoke from the burning fat would cling to the walls and ceilings, leaving behind a black residue that still stains ancient dwellings to this day, giving archaeologists a clear sign of their use. Though incredibly simple, these devices effectively extended the day and made indoor life possible during the long, dark nights. Archaeological finds have uncovered beautifully carved stone lamps, sometimes shaped like animals, or adorned with abstract symbols, revealing that they often carry deep spiritual significance as well as practical, everyday use. The warmth and flicker of these small, smoky flames offered a sense of companionship and safety against the vast night. Each small lamp was a contained, tamed fragment of the sun, brought inside to rest upon a hearthstone, whispering quietly while the world outside lay in shadow. Fire temples once burned flames that were never allowed to go out. In parts of ancient Persia, in Zoroastrianism, and India, sacred fires were meticulously tended and kept burning continuously, sometimes for centuries. These temples were built around eternal flames that symbolized ultimate truth, purity, and the divine, unending order of the cosmos. Priests were assigned to guard them day and night, feeding the fire with precise offerings of blessed wood or oil to maintain its perfect, steady balance. The constant, uninterrupted burning of the flame represented the unbroken connection between the material, human world and the spiritual, divine realm. Worshippers believed that to allow the sacred fire to die was to break a cosmic covenant and invite chaos. Some of these eternal flames still exist today, either burning from natural gas vents that were deemed sacred or painstakingly preserved through countless generations of devotion. They stand as one of the earliest and most powerful expressions of humanity's reverence for light as a living, divine force. Within those ancient, sacred walls, the steady glow was more than just warmth or brightness. It was the physical embodiment of continuity, a single flame that outlasted empires and carried the living memory of belief itself. Mythologies across the entire world described gods or heroes who stole fire for humankind. The gift of flame and the story of its acquisition appears in countless origin stories, from ancient Greece to Polynesia to the indigenous cultures of the Americas. In Greek legend, the Titan Prometheus defied the authority of Zeus to bring fire down from Olympus to humanity, and for this act of compassion, he suffered an eternal punishment. In Polynesian tales, the trickster hero Maui famously stole fire from the underworld, hiding it in the trees. In many Native American myths, animals like the coyote or the raven conspired to capture fire from its original guardians for the benefit of the first people. These recurring stories reveal a universal, cross-cultural recognition of fire as something both divine and incredibly dangerous. To possess it was to share in the power of creation itself, a power previously reserved for the gods. Fire symbolized both forbidden knowledge and righteous rebellion, the very spark that separated humans from the rest of the animal kingdom. The mythical theft of flame became the symbolic moment when human intelligence and spirit fused, marking the true dawn of civilization. Through these powerful legends, every culture acknowledged the same fundamental truth, that fire is both a blessing and a burden, forever entwined with the human soul. Wildfire is an ancient, essential part of the planet's life cycle. Long before humans ever existed, lightning strikes ignited vast forests and open plains, setting off natural, recurring cycles of destruction and renewal. These natural fires played a critical role in shaping ecosystems by clearing out old, dead vegetation, releasing trapped nutrients back into the soil and making space for new growth to begin. In fact, many plants evolved to depend on these fires for their very survival. Their seeds, for example, might wait patiently for years, sealed tight until the intense heat or the chemical signature of smoke signals the perfect time to sprout. Even the atmosphere itself bears the chemical imprint of ancient fire, enriched by the gases produced in millennia of flames. To our modern eyes, a wildfire often seems purely destructive, a catastrophe. But in the grand scheme of nature, it is a crucial part of balance. Forests and grasslands are living, dynamic systems that require periodic disturbance to remain healthy and thrive. Fire effectively resets the clock of the landscape, ensuring biodiversity and regeneration. Each blaze is a chapter in the planet's long story, a powerful reminder that creation and destruction have always been partners in the grand, unending rhythm of life. Some plants depend on intense heat to release their seeds. In regions of the world that are prone to fire, evolution has produced a remarkable and counterintuitive strategy for survival. Certain plants produce cones or hard seed pods that remain tightly sealed, often by a strong resin, until they are exposed to the intense heat of a wildfire. When a fire sweeps through the landscape, the extreme heat melts the resins or cracks the hard protective shells, allowing the seeds to be released onto the newly cleared ground. This ground, now free of competing plants and covered in nutrient-rich ash, is the perfect environment for them to germinate. This remarkable adaptation ensures that the new generation of plants begins to grow at precisely the moment when competition for sunlight and resources is at its lowest, and the soil is freshly fertilized. Species like the giant sequoia, the lodgepole pine, and many types of banksia in Australia thrive on this fiery cycle. Without periodic burning, their reproduction would slow dramatically or even cease altogether. In this way, fire becomes a partner in life rather than just an enemy. The forest burns, but the next generation waits patiently within it, ready and waiting to rise from the ashes. Through this incredible bond between flame and renewal, nature turns destruction into a moment of opportunity, proving that survival sometimes depends on surrendering to the heat. Certain pine cones are designed to open only after being scorched. High in mountain forests and across vast, dry plains, some species of pine trees guard their future seeds inside cones that are sealed shut with a tough, durable pitch. These resin-sealed cones can hang on the branches for many years, closed and waiting, until a fire passes through. When the flames sweep through the forest canopy, the intense heat softens and melts the resin, allowing the scales of the cone to spread apart and release the seeds stored safely inside. The ground below, which is now cleared of all the underbrush and coated in a fresh layer in mineral-rich ash, becomes the perfect nursery for these seeds to take root. This specialized relationship between the tree and the flame, known as serotiny, has existed for millions of years. The trees have come to rely on fire not just to reproduce, but to shape the very habitat that they inhabit. Without this periodic burning, the forest floor would become choked with competing undergrowth, and the pine seeds would never find the bare, sunlit soil they need to sprout. Every serotinous pine cone that opens in the quiet aftermath of a fire is a living symbol of adaptation, showing how life learns not just to survive adversity, but to use it to grow. Grasslands rely on periodic burning to stay fertile and healthy. Across the vast savannas of Africa, the prairies of North America, and the steppes of Eurasia, natural fire acts as a cleansing and renewing force. The flames move quickly, removing the buildup of dead, dry vegetation, recycling valuable nutrients back into the earth and preventing trees and shrubs from encroaching on and overtaking the open plains. After a burn, the grasses regrow almost immediately, nourished by the fresh ash and the newly available sunlight. Animals often return soon after, drawn to the tender, nutrient-dense shoots that emerge from the blackened earth. Many indigenous cultures recognize this vital rhythm and practice controlled, intentional burning to maintain the land's balance and productivity. Without the intervention of fire, these grasslands would eventually transition into forests, losing the unique biodiversity that depends on the open space. These ecosystems evolved over millennia alongside the presence of flame, and their continued fertility depends on it. Fire is not an intruder in these landscapes, it is a gardener, pruning and feeding the land in cycles that are far older than humanity itself. The vibrant green waves of new growth that follow a burn are the Earth's quiet, powerful expression of renewal. Lightning strikes start thousands of natural fires every single day around the world. At any given moment, somewhere on Earth, lightning is striking the ground, igniting countless small fires in forests, deserts, and grasslands. Most of these small fires extinguish quickly on their own, but some, under the right conditions of drought and wind, grow into vast blazes that can shape entire ecosystems. These events form a direct and powerful link between the atmosphere and the ground, a raw exchange of energy. Each strike carries an immense amount of power, heating the air in its path to tens of thousands of degrees in a fraction of a second. When that intense, focused heat meets dry vegetation, the spark becomes a flame. Lightning-driven fire is one of the oldest and most fundamental natural processes on our planet, responsible for maintaining the balance of life long before humans ever appeared on the scene. Today, modern satellites track these lightning strikes daily, mapping global patterns that reveal how weather, climate, and vegetation all interact. What begins as a brilliant flash in the clouds becomes a terrestrial force that renews the Earth, reminding us that even destruction has a purpose in nature's grand, cyclical design. Fire creates and releases nutrients that feed the next generation of growth. When vegetation burns, the complex organic matter that once held nutrients locked within its structure breaks apart. This process releases essential minerals like potassium, calcium, and phosphorus, returning them to the soil in a simple, accessible form. These elements, now in the ash, dissolve into the rainwater and seep into the ground, where they can be easily absorbed by the roots of new plants. The result is often a sudden burst of fertility in the seasons immediately following a fire, which is often visible as lush carpets of green growth and wildflowers across a once blackened landscape. Even the ash itself acts as a mild fertilizer, helping to balance the soil's acidity and enriching it for new life. This natural recycling process ensures that nothing in the forest ecosystem is truly lost or wasted. Fire simply transforms the locked-up energy and matter into forms that are once again accessible to the living. What looks like total devastation is actually a vital part of a larger pattern of renewal, a planetary metabolism in which the flame plays an essential role. Every new sprout that rises from the charred soil carries within it the memory and the nourishment of the fire that fed it. Ash can neutralize acidic soil and promote the growth of new plants. After a fire, the fine grey powder that is left behind on the forest floor is much more than just a residue. It is chemistry waiting to restore balance to the ecosystem. Ash contains alkaline minerals, primarily calcium and potassium carbonates, which work to counteract the natural acidity in the soil, improving the growing conditions for many species of plants. When rain mixes with this mineral-rich dust, it creates a mild, alkaline solution that seeps deep into the ground, unlocking other trapped nutrients and encouraging beneficial microbial activity. Farmers and gardeners have long understood this, using wood ash to enrich their fields, echoing nature's own cycles. In forests, this neutralization effect helps new seedlings take root in places where the soil may have previously been too acidic for them to thrive. Even in volcanic regions, where massive eruptions coat the land in thick layers of ash, the eventual result is one of renewal and incredible fertility. The forest floor, blackened and seemingly silent, becomes a quiet laboratory of life. From this gentle chemistry, new vegetation emerges, proof that even in the immediate aftermath of a fire, the earth is already beginning to heal itself. Birds have been seen carrying burning sticks to flush prey from hiding. In certain parts of Australia and Africa, particular species of raptors, such as black kites and brown falcons, have been observed picking up smouldering or burning branches from the edges of wildfires and deliberately dropping them into unburned areas of grass. This remarkable and intentional act spreads the flames, creating a new fire front. This action forces insects, lizards, and small mammals to flee their hiding places into the open, where the birds can easily catch and eat them. Indigenous peoples of Australia have known of this behaviour for centuries, even incorporating these firehawks into their mythology. Scientists who have recently documented this behaviour confirmed that it is one of the few known and reliable cases of animals, other than humans, manipulating and using fire as a tool for hunting. The sight of a bird wielding a burning stick blurs the line between pure instinct and genuine intelligence, revealing a cunning and sophisticated adaptation to an ancient, powerful force. Fire, in this context, becomes a part of the natural hunting strategy, shaping animal behavior just as profoundly as it shapes the landscape itself. The partnership between the predator and the flame is one of evolution's most astonishing and clever collaborations. Some beetles can detect the infrared heat of distant fires. Certain species of fire beetles possess extraordinary and highly specialized sensory organs that allow them to detect the infrared radiation, the heat produced by forest fires from many kilometers away. They are drawn to the fire and will fly toward the heat, not away from it. This is because the freshly burned, dead or dying wood is the perfect and safest place for them to lay their eggs. Their larvae then feed on the weakened trees and charred bark, thriving in an environment where their own predators cannot survive and competition is scarce. These beetles are equipped with tiny, pit-like infrared receptors, so incredibly sensitive that they can sense minute temperature changes smaller than a single degree. Their natural ability often surpasses that of many human-made infrared detectors. In a way, these creatures have evolved to follow fire just as other animals might follow the scent of water or the sight of light. This unique adaptation ensures their survival in an environment that is defined by periodic burning. The beetle's strange attraction to intense heat shows just how deeply fire is woven into the very fabric of life, guiding even the smallest creatures through its endless cycles of destruction and renewal. Fire changes landscapes faster than erosion or rain. While the forces of wind and water slowly and gradually shape the surface of the earth over millennia, fire works in moments. A single, large blaze can fundamentally alter entire ecosystems, stripping away vegetation, exposing bare soil to the elements, and changing the chemistry of the air and ground almost instantly. Hillsides are blackened, dense forests are opened up to the sun, and new patterns of life begin to emerge within a matter of days or weeks. In some cases, repeated burning over many centuries can create and maintain permanent biomes, such as the world's great savannas and shrublands. The rapid, dramatic transformation caused by fire rivals many geological forces in its sheer impact, yet it operates on a human timescale, fast enough for us to witness. Afterward, the landscape does not simply return to what it was before, it becomes something new, a landscape shaped by both the loss of the old and the potential for the new. The sheer speed of this process reveals how powerfully energy can remake the planet, reminding us that change does not need to be slow to be profound. Fire is Earth's sudden sculptor, carving renewal directly out of devastation. Desert ecosystems use small, infrequent fires to maintain their balance. In the vast, arid dryness of deserts, fire appears rarely, but it serves a critical role when it does. The sparse vegetation, consisting of scattered shrubs and hardy grasses, can burn in brief, quick flashes, clearing away dead material and encouraging the growth of new, tender shoots. These small fires recycle the few available nutrients back into the thin, poor soil, allowing life to persist in environments that often seem barren. Many desert plants have evolved to cope with this, developing thick, protective bark, waxy leaf coatings, or seeds that can resist the heat, enabling them to survive and regenerate quickly after a fire. The animals of the desert too have adapted to this rhythm, often burrowing deep underground or fleeing to rocky, fireproof shelters until the land cools down again. By removing the old, dead growth and stimulating new life, fire prevents a few plants from outcompeting all others for the scarce resources of water and sunlight. Without it, the desert could slowly choke in its own dryness. Even here, in one of the world's most fragile and seemingly fire-resistant ecosystems, the flame plays the part of a quiet, patient gardener, keeping the delicate balance through periodic renewal. Charred forests can cool the soil and help trap moisture. After a wildfire has passed, the blackened, skeletal remains of trees might look lifeless and desolate, yet they serve a vital ecological purpose. The dark, carbon-rich residue left behind, the charcoal and ash, forms a thin, protective layer over the ground. This layer is surprisingly effective at absorbing rainfall and holding it in the soil, preventing it from evaporating too quickly. Beneath this charred blanket, surviving roots, seeds, and microorganisms find a crucial refuge, insulated from the harsh, direct sunlight above. The burned wood itself acts like a sponge, slowing evaporation and preserving precious moisture through the critical early stages of the forest's regrowth. Over time, mosses and fungi will begin to colonize the cooled, damp earth, beginning the slow, steady process of restoring life. Scientists who study these post-fire ecosystems have found that the soil beneath the charred surface can often retain more water than unburned areas nearby. This paradox clearly shows how the act of destruction can create the very conditions necessary for recovery. A blackened forest floor may appear silent and dead, but within it lies the hidden, resilient pulse of renewal, waiting patiently for the return of rain and sunlight. Fire shapes the migration paths of animals across continents. For countless species, from insects to large mammals, the presence or absence of fire determines when and where they move. Large grazing animals, like bison or wildebeest, will follow the fresh, green, nutrient-rich shoots that spring up in the weeks after a burn, finding excellent nourishment in the renewed growth. Birds of prey and various scavengers will often gather at the active edges of a flame front, hunting the insects, rodents, and small animals that are fleeing the heat and smoke. Even the great seasonal migrations in Africa and historically in North America often followed seasonal burn patterns, with the herds moving in harmony with the natural cycles of fire and regrowth. Over long periods of time, these fire-driven patterns carve invisible trails across the land, guiding herds, flocks, and their predators alike. In this way, fire becomes a living map, written in light and ash, directing the flow of life towards sustenance. It is not only a force of destruction but also a powerful shaper of movement, influencing the fundamental rhythm of entire ecosystems. When the flames finally fade, life begins its journey anew, tracing paths that were first drawn by the flicker of ancient fires across the plains. Smoke particles can seed clouds and influence rainfall patterns. When a large fire sends massive plumes of smoke into the sky, it releases billions of tiny, microscopic particles that can drift high into the atmosphere. These microscopic bits of ash and carbon are known as condensation nuclei. They provide a physical surface, giving water vapor something to cling to. In time, clouds can begin to form around these smoke particles, thickening into storm systems that may eventually release rain. Some regions, in fact, experience increased rainfall downwind of large fires as the smoke changes the way sunlight and heat interact with the atmosphere. However, the effects are not always beneficial. If there is too much smoke, the dense cloud of particles can block sunlight, cooling the air and actually preventing clouds from forming at all. The balance is incredibly delicate, and atmospheric scientists study these complex interactions to understand how fire can alter climate patterns on both a local and a global scale. What rises from the ground as a sign of destruction can, under the right conditions, return as a gift of renewal, as rain falls back upon the scorched earth it was born from. Some fungi thrive only on burned ground. Hidden beneath the ashes of a forest fire, certain specialized species of fungi awaken. Their spores can lie dormant in the soil for decades, patiently waiting for the intense, triggering heat and the specific chemical changes in the soil that only a fire can bring. Once the ground is cooled, they emerge rapidly, sending up dark, distinctive fruiting bodies, mushok arms, that are perfectly adapted to feed on the charred, carbon-rich remains of plants and wood. These pyrophilous or fire-loving fungi play a crucial ecological role by being the first to break down the tough, carbonized material, returning its nutrients to the soil so other plants can use them. Some, like the highly prized morel mushroom, are famous for flourishing in burned landscapes, often forming symbiotic relationships with the roots of fire-damaged trees. For foragers and ecologists alike, the appearance of these fungi is a hopeful sign that the process of recovery has already begun. In a place that looks utterly ruined to the human eye, new life is already busy rewriting the soil's chemistry. Fire may clear the surface, but just below it, these resilient hidden organisms are turning destruction back into fertile possibility. Prairie fires once stretched across thousands of miles. Before widespread human settlement and agriculture transformed the landscape, the vast native prairies of North America burned regularly in immense natural fires, ignited by lightning that could travel uninterrupted for weeks at a time. Lightning strikes and dry, powerful winds would set entire grasslands alight. But these fires rarely destroyed the ecosystem. Instead, they were the force that renewed it. The native prairie grasses evolved to not only survive these fires but to thrive because of them, using deep, protected root systems that survived unharmed below the heat. Vast herds of bison, antelope, and countless other species followed the regrowth, feeding on the tender, nutrient-rich shoots that appeared in the wake of the flames. The smoke from these ancient, continent-spanning fires would have carried for thousands of miles, a seasonal marker of the cycle of rebirth that defined the prairie's very life. The indigenous peoples of the plains understood this rhythm intimately and used their own controlled burns to mimic it, maintaining the balance and abundance of the land. The modern landscape has been quieted, but deep in its soil remains the chemical memory of fire's vast passage, the ancient echo of the element that once brushed its hand across entire continents in a blaze of golden flame. Savannas evolved to burn regularly without being destroyed. In the tropical and subtropical regions of the world, the combination of seasonal grasses, scattered trees, and distinct wet and dry seasons creates ecosystems that depend on frequent fire for their existence. Savannas are not devastated by this burning, they are renewed by it. The grasses regrow within days of the fire, nourished by the fresh layer of ash and the newly opened sunlight. Meanwhile, the mature trees, protected by thick insulating bark, survive and sprout new leaves. The fire prevents a dense forest canopy from forming, thus preserving the wide, open plains that support iconic wildlife like elephants, lions, giraffes, and vast herds of antelope. Without the periodic intervention of flame, these unique landscapes would change entirely, slowly succeeding into dense woodlands and losing their defining character. Scientists studying savannas have found that even lightning strikes alone are frequent enough to maintain this delicate balance, shaping the pattern of life over millennia. In these ecosystems, fire acts as both a boundary and a sculptor, keeping open what would otherwise close. In every flicker of flame across the savanna horizon lies the quiet, ancient collaboration between earth, rain, and fire, an eternal partnership that ensures the land can continue to breathe. Ancient lightning fires may have created the first patches of open grassland. Millions of years ago, as the world's climate naturally grew drier and cooler, lightning began to strike more often across wooded plains and sparse forests. The fires that followed would have cleared large patches of trees and shrubs, leaving behind open, sunlit spaces where hardy grasses could thrive. These early, fire-cleared zones eventually became the cradles of the world's great savannas, prairies, and steppes, ecosystems that still dominate much of the planet's landmass today. The animals that lived in these regions evolved alongside the presence of fire, adapting to grazing behaviors and migration patterns that were shaped by the fire's predictable rhythm. In this way, lightning acted as both a destroyer of forests and an architect of grasslands, sparking the massive ecological transformation from dense, shady woods to open, sun-drenched plains. Fossilized soils from this period show distinct layers of charcoal that mark this critical turning point in Earth's history. What began as a random natural event, a lightning strike, grew into one of the most influential and powerful processes in all of ecology. Through fire, the planet learned to balance the dominion of trees with the resilience of grass and shadow with open light. Charcoal from old wildfires helps to store carbon in the soil for centuries. When wood burns incompletely, as it often does in a wildfire, it leaves behind charcoal, a stable, porous form of carbon that is highly resistant to decay. Instead of releasing its stored carbon back into the atmosphere as CO2 as it would during normal decomposition, this substance, known as biochar, remains locked safely in the soil, often for hundreds or even thousands of years. Scientists have discovered that the presence of this biochar can significantly improve soil fertility and water retention, all while acting as a long-term carbon sink, moderating the climate by keeping carbon out of atmospheric circulation. The forest floors around the world hold vast, ancient stores of this natural charcoal, silent, dark archives of past fires that are still influencing the chemistry and health of the Earth today. In recent years, researchers and farmers have begun recreating this natural process deliberately, using controlled burns or pyrolysis to create biochar for use in sustainable agriculture. What nature discovered by accident, humanity is now relearning to use as a tool for ecological balance. Each dark layer of charcoal hidden beneath our feet is a reminder that even the residue of a fire has a profound purpose, storing the memory of the past and nurturing the life of the future within the soil itself. Fire can act as both a destroyer and a creator in every single ecosystem. Nowhere in the natural world is this duality more visible than in the behavior of a flame. It consumes, yet it renews. It clears away the old, yet it nourishes the new. In forests, prairies, deserts, and even wetlands, the very same process that devastates one generation of life is simultaneously preparing the ground for the next. Seeds that require heat to open, fungi that feed exclusively on char, and animals that follow the fresh regrowth all depend on what first appears to us as total ruin. Without the disturbance of fire, many ecosystems would stagnate, overgrow, and ultimately lose their vitality and diversity. With fire, a dynamic balance is restored. Every blaze completes a cycle that mirrors the process of creation itself, a place where endings and beginnings are not separate but coexist in the same moment. Scientists who study the field of fire ecology find that even the specific timing, frequency, and intensity of burns are perfectly tuned by evolution to the needs of the landscape. The element that once terrified early humanity is now revealed as one of the oldest and most essential tools of life, shaping the planet's endless renewal with every single spark that meets the air. Fire requires three elements: heat, fuel, and oxygen. Every single flame, from the tiniest flicker of a candle to a raging inferno, depends on a perfect, interconnected triad of components known as the fire triangle. Heat is required to initiate the reaction and bring the fuel to its ignition temperature. Fuel is the matter that will be consumed. And an oxidizer, typically oxygen from the air, is needed to sustain the chemical reaction. If you remove any one of these three elements, the process of combustion ends instantly. This simple fundamental balance explains why damp wood only smolders instead of burning. The heat is lost to vaporizing water, or why a flame is extinguished when placed under a blanket or doused in foam. The oxygen is cut off. In controlled environments such as car engines or industrial furnaces, this principle allows for the precise manipulation of temperature and power. The fire triangle also serves as a symbol for how energy itself depends on harmony. Too much of one element can lead to chaos and explosion, while too little leads to failure and cessation. Understanding this delicate interplay gave humanity its earliest scientific insight into the nature of combustion. Every spark in the universe obeys this rule, from the smallest, glowing ember to the most distant, massive star, which burns through its own cosmic version of this eternal three-part equation. Fire, in all its forms, is the art of perfect balance, sustained through the laws of chemistry. Removing any one of these elements, heat, fuel, or oxygen, stops the process of combustion instantly. Fire can survive only when its three vital components coexist in the right proportions. If the heat drops below the material's ignition temperature, the chemical reaction ceases. If the fuel source is completely exhausted, nothing remains to be consumed. If the supply of oxygen is cut off, the chemical chain reaction collapses. This fundamental principle forms the basis of all firefighting and fire prevention strategies. Water is effective because it absorbs an immense amount of heat, robbing the fire of its temperature. Fire blankets or chemical foam work by smothering the flame, cutting off its supply of oxygen. Fire breaks, which are gaps cleared of vegetation, work by removing the fuel from the fire's path. The very moment one side of the fire triangle disappears, the entire process cannot continue. In this way, even the most ferocious and seemingly unstoppable blaze can be subdued through a simple understanding of its essential needs. The apparent fragility of a flame is hidden beneath its appearance of overwhelming strength. It depends entirely on its surrounding conditions, thriving only when nature's balance allows it. To extinguish a fire is not truly to destroy it, but rather to unmake the specific circumstances that were required to sustain it. It is a powerful reminder that even the most powerful forces can vanish in an instant when their balance is lost. Some reactions mimic fire without producing a visible flame, such as the rusting of iron. Oxidation, the chemical process at the heart of fire, does not always glow or blaze with heat. Yet, it follows the exact same principles that govern burning. When a piece of iron rusts, its atoms are slowly combining with oxygen and water, releasing energy so gradually that no perceptible heat or light can form. Over a long period of time, the solid metal transforms into a flaky, reddish oxide, a solid, brittle version of combustion that has been stretched out across years instead of unfolding in seconds. This process proves that fire and rust are not different things, but are rather part of a single continuum of chemistry, separated only by their speed. Even in the profound stillness of corrosion, the very same exchange of electrons is occurring, linking the quiet, slow decay of a piece of metal with the brilliant, rapid radiance of a flame. This slow fire shapes our landscapes and our industries alike, silently carving ships, bridges, and machines back into powder. In both the bright flame and the silent rust, matter is simply seeking equilibrium, releasing its stored chemical energy until it becomes stable once more. Phosphorescent reactions are like chemical fires that produce no heat. In certain chemical reactions, energy is released not as warmth but purely as light. This gentle, cold glow, known as phosphorescence or chemiluminescence, appears in certain minerals, in deep ocean creatures, and in laboratory mixtures. Fireflies, for instance, produce their familiar light through a precise and highly efficient chemical reaction that wastes almost no energy at all in the form of heat. The result is a cool, soft radiance, a flame in its essence, but not in its temperature. In the dark depths of the ocean, countless organisms use this cold fire to communicate, to hunt, or to hide, painting the utter darkness with shifting, ghostly constellations of blue and green. Scientists actively study these reactions to create more efficient forms of lighting and new medical imaging technologies. These processes reveal that combustion is only one of a number of ways for matter to shine. Within the quiet chemistry of phosphorescence lies a peaceful, gentle counterpart to the burning flame. It is light born from transformation, but untouched by the destructive power of heat. It is nature's quiet fire, glowing softly without consuming the world around it. Combustion in pure fluorine gas is far more violent than in oxygen. Fluorine is the most reactive chemical element known, and when it is used as the oxidizer in a combustion reaction, in place of oxygen, it produces results that are beyond imagination. Almost any material, even substances that we consider non-flammable and that resist normal burning like glass, sand, or even asbestos, can ignite spontaneously and violently when exposed to fluorine gas. These reactions release enormous, uncontrolled amounts of energy, often accompanied by blinding flashes of light and clouds of highly corrosive gas. Because the fluorine atom bonds so eagerly and aggressively with other elements, it can tear other molecules apart in an instant. Scientists must handle it with extreme caution, studying its properties only in specially designed, reinforced chambers. In theoretical rocket propulsion systems, fluorine could outperform oxygen as a fuel oxidizer, providing much greater thrust. However, its extreme volatility and toxicity make it impractical for most uses. Its behavior demonstrates the absolute outer limits of combustion chemistry. Fire, in this form, is no longer gentle or even visible in a familiar way. It is pure, raw reaction, the most intense and violent expression of matter's fundamental desire to combine. Hydrogen burns with a nearly invisible, pale blue flame. When hydrogen gas reacts with oxygen, it forms simple water vapor, H2O, and releases a significant amount of heat. Yet, the flame it produces is so clean that it can barely be seen in daylight. The reaction is so efficient that almost no carbon particles or glowing soot are created to color the light. The faint, pale blue hue that is sometimes visible comes directly from excited H2O and OOHO molecules emitting photons as they form and cool. Because the flame is so difficult to see, hydrogen fires are notoriously difficult to detect without specialized thermal or UV sensors, which poses unique safety challenges. Despite this, hydrogen is widely considered a potential fuel of the future duetto, its efficiency and its abundance in the universe. Its combustion produces only water as a byproduct, making it one of the cleanest and most environmentally friendly energy sources imaginable. The ghostly, almost invisible flame of burning hydrogen represents the quiet, immense potential of chemistry, harnessed without pollution. It is a mere whisper of energy that embodies both purity and power. Liquid oxygen can make ordinary organic materials explode on contact. When common flammable substances like paper, oil, or fabric come into contact with pure liquid oxygen, they absorb it rapidly, becoming saturated with one of the most reactive elements in existence. If these super oxygen-rich materials are then disturbed, even by a small spark, simple friction, or a physical impact, it can set off a violent, devastating explosion. The reason lies in the concentrated chemistry. The stored pure oxygen feeds the combustion reaction so quickly and completely that all the energy is released in a fraction of a second. Engineers who handle rocket fuels, where liquid oxygen, or LOX, is a common oxidizer, or cryogenic systems must take extraordinary precautions to prevent such contact. In spaceflight, liquid oxygen serves its purpose as an oxidizer, enabling engines to burn fuel at extreme temperatures. Yet outside of those controlled systems, its touch is perilous. It has the power to turn ordinary, everyday matter into a high-potential fuel, just waiting for the smallest trigger to unleash its energy. This combination of intense beauty and extreme danger defines much of fire's fundamental nature. It is a delicate, precarious balance between creation and catastrophe. Sodium burns with a bright, intense yellow because of its atomic spectrum. When sodium atoms are heated in a flame, their outermost electron absorbs the energy and jumps to a higher, excited energy level. It immediately falls back to its original level, and in doing so, it releases that extra energy as a photon of light at a very specific wavelength. That wavelength corresponds to a deep golden yellow, one of the most recognizable and distinct colors in all of chemistry. This is the same spectral line that colors high-pressure sodium streetlights and gives a brilliant yellow to fireworks. It also appears in laboratory flames whenever sodium is present, even in the most minute trace amounts. This process clearly reveals the intimate relationship between fire and quantum physics. Every element on the periodic table emits light according to its own unique atomic structure, creating a fingerprint. This unique signature allowed scientists to identify substances by their flame color long before modern, sophisticated instruments existed. The characteristic glow of sodium is both a scientific tool and a symbol of the order hidden within the chaos. Inside the seemingly random flickering motion of a flame, the universe reveals its underlying precision, turning raw energy into light of a perfect and predictable beauty. Different metals create distinct flame colors, which are used to create fireworks. Fireworks are, in essence, chemistry painted across the night sky. Strontium salts are used to produce deep, vibrant reds. Barium compounds give brilliant greens. Copper creates rich blues, and sodium, of course, glows with its signature yellow. When these metal salts are heated by the fireworks explosion, the atoms in the metals release photons at their own characteristic wavelengths, producing the vivid, colorful palette that fills the sky during celebrations. Each color requires a careful, precise balance of temperature and chemical composition. If the reaction is too hot, the distinct hues can wash out into a generic, brilliant white. Ancient alchemists and pyrotechnists first noticed these color variations while heating different minerals in their furnaces. But it was modern chemistry that turned this simple observation into a spectacular art form. Today, chemists and engineers design fireworks with astonishing precision, using complex mixtures of oxidizers, fuels, and metallic salts to choreograph breathtaking explosions of light, sound, and color. The spectacle is far more than just entertainment. It is chemistry expressed as pure beauty, a powerful reminder that even the most joyful and dazzling bursts of color come from the controlled, intentional mastery of fire's elemental language. Fireworks are precisely engineered explosions of powdered chemistry. Inside every single fireworks shell lies a carefully arranged and complex system of fuel like charcoal or sulfur, an oxidizer like potassium nitrate, and various color-producing metal compounds. When the main fuse is lit, a timed sequence of reactions first launches the shell skyward with a lift charge. Then, a separate internal time delay fuse detonates the main burst charge at a precise altitude. This explosion spreads burning pellets, known as stars, across the air, with each star glowing intensely with a color based on its unique chemical makeup. Engineers meticulously calculate the size, pattern, and delay of each burst, using a combination of mathematics and pyrotechnic science. Even the sound of the explosion, the loud bang or the crackling effect, is intentionally designed by modifying the casing thickness and the chemical composition. Though their stunning beauty lasts for only a few seconds, fireworks represent centuries of human experimentation in the fields of combustion and control. They are among humanity's purest and most joyful collaborations with chemistry, transforming simple, dull powders into fleeting moments of collective wonder. Every brilliant, colorful bloom that fades against the dark sky is a reminder that technical knowledge and artistry can coexist perfectly within the very heart of a controlled fire. Candle flames contain countless micro-explosions happening every second. To the naked eye, a simple candle flame appears soft, steady, and continuous. Yet, if you were to view it with high-speed photography, it would be revealed as a chaotic field of endless, microscopic detonations. Each individual glowing particle of carbon soot ignites and is extinguished in mere fractions of a second, releasing tiny, individual bursts of light and heat before vanishing completely into invisible gas. These miniature, fleeting explosions are the very essence of combustion. They are countless, tiny individual events that all merge together into what our slow eyes perceive as a steady, stable fire. The sound they produce is far too faint for us to hear, but together, all at once, they produce the gentle, hypnotic shimmer and flicker that we find so mesmerizing and calming. Every moment, new molecules of wax vapor are being formed, broken apart, and reformed in a perfect, self-sustaining rhythm that keeps the flame alive. What appears to us as calm and still is, in truth, a microscopic storm of chemical motion, a quiet, intricate orchestra of reactions dancing just above the wick. In its delicate, peaceful glow, the candle hides a universe of restless, vibrant energy. Soot is simply carbon that escaped complete combustion. When a flame burns without a sufficient supply of oxygen, not all of the fuel molecules are able to fully react. The leftover carbon atoms, which haven't found oxygen partners, condense into tiny, solid black particles known as soot. These microscopic grains rise up through the hot air, glowing orange or yellow for an instant, which is the light we see before they cool down and drift away as dark smoke. In ancient times, this soot would collect on the ceilings of caves and temples, marking the first and most enduring physical record of human fire use. Artists later learned to collect this soot, grinding it and mixing it with binders to create the first black inks and paints, literally transforming a waste residue into lasting beauty and communication. Though the particles are tiny, soot has a large impact on everything from air quality to global climate, as the dark particles absorb sunlight and warm the atmosphere. Its very presence tells a story of imbalance, a fire that was deprived of the breath it needed. Scientists today study how to reduce soot in engines and stoves, aiming to make combustion cleaner and more efficient. Each dark particle is a tiny fragment of an incomplete transformation, a reminder that even in a flame, perfection depends on a delicate harmony between fuel, heat, and air. A flame's shape reveals the speed of its chemical reaction. Every flame is a living, visible graph of its own chemistry in motion. The sharper and more elongated the flame, the faster the chemical reaction is occurring. In a calm, stable candle flame, the shape tapers smoothly upward as the hot gases rise slowly and fresh oxygen is drawn gently inward. In contrast, during an explosive burn where fuel and air are mixed violently and rapidly, the flame front expands into jagged, unstable patterns or even propagates as a shock wave. Scientists use high-speed cameras and techniques like spectroscopy to study these complex forms, reading their motion and shape like a language. The curves, the flickers, and the sharp edges all encode detailed information about the velocity of the molecules and the transfer of heat within the reaction. Even small, subtle variations in the surrounding air pressure or humidity can change the entire structure of the flame. What the human eye perceives as simple beauty, science can read as complex data. A flame's shape is a unique signature of its energy, a fleeting, momentary portrait of matter in motion, drawn in light and erased by air, all within the span of a single breath. In microgravity, flames form perfect spheres of diffusion. Without the force of gravity to pull heavy, cool air down and allow light, hot air to rise, a flame no longer flickers or stretches into its familiar teardrop shape. Instead, it becomes a glowing sphere, perfectly steady and symmetrical, fed only by the slow, random process of gas diffusion. Inside space stations, astronauts have meticulously studied these spherical flames to understand the fundamentals of combustion in its purest, simplest form. The shape reveals how fire behaves when it is completely freed from the powerful influence of convection, a state where heat does not rise and cool, air does not fall. The result is a fire that is almost silent and perfectly still, looking like a miniature, ghostly sun floating in the air. These spherical flames tend to burn more efficiently and at much lower temperatures than their counterparts on Earth, offering valuable clues for designing cleaner, more efficient engines and fuel systems back home. Watching them drift serenely in microgravity is like observing a living star, a perfect object suspended halfway between the realms of chemistry and art. In that weightless, quiet chamber, the everyday laws of fire are rewritten, showing that even the simplest spark becomes something cosmic and strange when gravity finally releases its hold. Scientists study these spherical flames to understand how fires spread. In the unique, weightless environment of space, flames are forced to reveal their innermost secrets. When a fire is lit in microgravity, the absence of the upward flow of convection allows researchers to observe the combustion process as if in slow motion. This exposes the fine, subtle details of how gases mix and how the chemical reactions actually propagate. By studying these stable, spherical flames, scientists can create more accurate models of how fire travels through different materials and in different environments back on Earth. These experiments are crucial for improving spacecraft safety, but they also guide significant advances in energy efficiency, modern engine design, and pollution control. The even, steady burn of a spherical flame shows what happens when convection is completely removed from the equation, leaving only molecular diffusion to carry oxygen to the fuel. It is the purest, most fundamental version of fire, stripped of all turbulence and chaos. By observing its smooth, stable glow, researchers are witnessing the fundamental language of combustion, the very same processes that shape distant stars, power our engines, and even cause the simple flicker of a candle at home. Under extremely high pressure, even carbon dioxide can support combustion. At ordinary, everyday conditions, carbon dioxide is a fire extinguisher. It smothers flames by displacing the oxygen they need to burn. Yet, under conditions of immense pressure and extreme heat, this seemingly inert molecule can be forced to behave very differently. Experiments have demonstrated that in certain high-pressure mixtures, the carbon dioxide molecule, CO2, can be broken apart, releasing its oxygen atoms, which can then go on to sustain brief, strange flashes of combustion with a fuel like magnesium. These unusual reactions occur in conditions that are similar to those found deep inside planets or during certain high-energy industrial processes. This discovery challenges the simple view of carbon dioxide as a passive, non-reactive gas, revealing its hidden potential to become an active participant in combustion when put under extreme stress. Studying these phenomena helps scientists to better understand the atmospheric chemistry on distant, alien worlds, where pressures and temperatures far exceed anything we experience on Earth. It shows that even the most stable and familiar compounds can reveal a hidden, reactive power when pushed to their absolute limits. In the deep, fundamental language of physics, no element is ever entirely dormant, only waiting for the right conditions to awaken. Flames can act as ion engines that push tiny particles of air. Inside a flame, the hot gas molecules are broken apart into charged particles called ions, which are positive, and electrons, which are negative. These charged particles respond to electric fields. When an electrical current is applied to a flame, these ions and electrons can be accelerated, colliding with neutral air molecules and creating a small but measurable thrust. Scientists refer to this phenomenon as ionic wind. This effect can be used to move objects lighter than a feather or to drive air through silent, microscale engines with no moving parts. The very same principle, on a larger scale, powers some advanced spacecraft propulsion systems, where ionized gases are expelled at high speed to generate a slow, steady motion in the vacuum of space. In laboratory settings, powerful electric fields can even be used to shape, bend, or flatten flames, guiding them like threads of light. Each flicker, in this case, becomes both a chemical reaction and an electrical phenomenon, a fascinating bridge between heat and motion. Though invisible to the human eye, these gentle ionic pushes reveal that fire is more than just light and warmth. It is a plasma in motion, capable of exerting a physical force and carrying energy in ways that hint at the future of propulsion. Cold flames burn slowly and silently at very low temperatures. There exists a strange type of flame that glows with a faint, ghostly blue light and feels almost cool to the touch. Known as cold flames, they occur when fuel and oxygen react so gradually and inefficiently that the temperature stays far below the normal ignition point, often just a few hundred degrees. They are nearly invisible in daylight and emit very little heat, yet they represent a true self-sustaining combustion reaction. In engines and chemical reactors, these delicate, cool reactions often appear as an intermediate stage just before full hot ignition occurs, revealing the complex, multi-stage process of how burning actually begins. Scientists carefully study cold flames to find ways to improve fuel efficiency and reduce harmful pollutants, since they demonstrate how to achieve a slow, controlled energy release with minimal waste. Their discovery proved that fire does not necessarily need roaring heat or bright yellow light to exist. These quiet, ghostly flames demonstrate the profound subtlety of chemistry, a gentle, slow rearrangement of molecules that whispers instead of roars, proving that transformation can happen even in apparent stillness. Fire can turn sand into a synthetic stone called vitrified rock. When exposed to prolonged, intense heat, loose sand and soil can melt and fuse into a hard, glass-like material known as vitrified rock. This transformation occurs naturally in places where lightning strikes sand, forming fulgurites, or where lava flows over the ground, and it can be created artificially in industrial furnaces or during large accidental explosions. The intense heat fuses the silica and other minerals in the soil together, forming smooth, glossy, or bubbly surfaces that cool into a single, solid stone. Archaeologists have found vitrified walls in ancient fortresses across Europe, particularly in Scotland. This suggests that entire ramparts of stone and rubble were once intentionally subjected to deliberate, massive burning, perhaps as a defensive measure to strengthen them, as part of a ritual, or as an act of warfare to destroy them. The resulting fused material is highly resistant to erosion and remains solidly fused for millennia. In modern science, similar vitrification techniques are used to create durable synthetic stone for construction or to safely contain and immobilize hazardous waste. Each piece of vitrified rock tells a story of profound transformation, a moment where the raw earth was briefly turned liquid by fire and then frozen solid in that instant of change, becoming a permanent, glassy memory of the heat that made it. Lightning strikes can magnetize the soil through their intense heat and electric current. When lightning hits the ground, the temperature in the channel soars higher than the surface of the sun for a split second. The soil and minerals directly in the strike's path instantly melt and fuse into the glassy, hollow tubes we know as fulgurites. As these fragile, molten structures cool down rapidly, any iron-bearing minerals within them are aligned by the powerful magnetic field generated by the lightning's immense electric surge. This process locks in a faint but measurable magnetic field, a remnant magnetism. Scientists can study these tiny magnetic traces to learn the direction and intensity of the ancient strikes, effectively reading the history of past thunderstorms as it is recorded in the stone. The process also fundamentally alters the chemistry of the soil, creating new compounds and mineral phases that would never be able to form under ordinary everyday conditions. Each fulgurite is a frozen, sculpted path of raw energy, a delicate, glassy memory of the moment the sky met the earth. To hold one in your hand is to touch the direct, physical residue of an event that burned hotter and faster than anything the human hand could ever hope to create. Stars are cosmic fires, but they are powered by fusion instead of oxygen. The light of the stars, including our own sun, comes not from a chemical reaction like burning fuel in the air, but from a nuclear process deep within their cores. Under the crushing pressure of immense gravity, hydrogen atoms are forced together so violently that they fuse into helium atoms. This process, called nuclear fusion, releases colossal amounts of energy in the form of radiation heat and light. This is the same fundamental principle that humans are attempting to replicate and harness in experimental fusion reactors here on Earth. The very energy that keeps the stars shining for billions of years is the same energy that ultimately powers all life on our planet. Fire on Earth merely rearranges the bonds between molecules, but the fire in the stars reshapes the very atoms themselves. Each sunrise we witness is a direct gift of this distant fusion, a steady reminder that our planet is orbiting a living, breathing furnace that is vast beyond all imagination. When we gaze at the light of a simple campfire, we are seeing a faint, chemical reflection of the very same physics that burns in the hearts of the stars, a universal language of energy written in heat and brilliance. Some planets contain flammable chemicals that could ignite with a single spark. On other worlds, like Saturn's strange hazy moon, Titan, the atmosphere is thick and rich with methane and other hydrocarbons, which can condense and fall as rain. On its surface, vast rivers and lakes of liquid methane and ethane carve landscapes beneath cold, orange skies. If a significant amount of oxygen were ever present in that atmosphere, that entire world would be primed to erupt in flame. A single spark could ignite the atmosphere, and its entire surface could become a sea of fire. The profound, cold absence of free oxygen is what keeps it calm, a frozen, quiet mirror of chemistry just waiting for the right trigger. Scientists study such exotic environments to understand how planets evolve and how their atmospheres behave under truly alien conditions. The paradox of a place that literally rains fuel but can never burn captures the profound strangeness of the cosmos. Titan's gentle hydrocarbon rain reminds us that fire is not a constant in the universe. It is a delicate and perhaps rare balance between the right elements, the right pressure, and that one invisible critical moment when a reaction begins. Volcanoes on distant moons can erupt with sulfur flames. On Io, one of Jupiter's largest moons, active volcanoes blaze with yellow, blue, and red plumes of molten sulfur glowing across the frozen darkness of deep space. These relentless eruptions are driven not by internal heat from the moon's formation, but by the tidal forces of Jupiter itself. As Jupiter's immense gravity stretches and kneads Io's crust, it generates tremendous heat from friction. When sulfur gas escapes from these volcanoes and ignites, it burns in eerie, exotic colors that are rarely seen on Earth. Spacecraft that have photographed these eruptions, like the Voyager and Galileo probes, show fountains of glowing material rising hundreds of kilometers high, far above the moon's surface. Io's surface is constantly renewing itself under this alien fire, making it the most volcanically active body in our entire solar system. Watching these distant, silent flames is like witnessing the act of creation in another chemical language. They prove that fire is not confined to Earth's atmosphere, but thrives wherever energy and chemistry collide in the vast, complex machinery of the cosmos. The sun's corona, its outer atmosphere, blazes at millions of degrees. Surrounding the sun is a faint, ethereal halo of light known as the corona. It is visible to the naked eye only during a total solar eclipse or through specialized scientific instruments. Although it is farther from the sun's core, the corona is astonishingly, paradoxically hotter than the solar surface itself, millions of degrees Celsius compared to the mere thousands of degrees on the surface below. Scientists believe that the sun's complex, powerful magnetic fields twist, snap, and reconnect within the corona, releasing immense, sudden bursts of energy that heat the thin gas to these unimaginable temperatures. The corona is constantly streaming charged particles, a plasma, out into space, creating the solar wind. This wind travels through the solar system, shaping planetary atmospheres and painting the beautiful aurora, or northern and southern lights, across Earth's magnetic poles. It is a fire beyond fire, invisible to us most of the time, yet its energy touches every atom of life on our world. To look upon the corona during an eclipse is to see the delicate boundary between matter and pure energy, the place where the sun whispers its light and breath across the entire solar system. Meteor impacts can set forests ablaze even if the object vaporizes in the air. When a large meteor enters the atmosphere, it compresses the air in front of it at hypersonic speeds. This compression generates powerful shock waves and incredible heat, which can be intense enough to ignite forests on the ground before the rock itself even touches the surface. Even if the meteor burns away completely or explodes in the air, this blast of superheated air can trigger widespread fires across vast distances. Geologists can find evidence of this in layers of charcoal preserved in ancient sediments, marking catastrophic impact events that altered global climates and reshaped entire ecosystems. The famous Tunguska explosion in Siberia in 1908, for example, leveled thousands of square kilometers of trees without leaving an impact crater, its fiery shockwave sweeping across the wilderness. Such events remind us that fire from the sky, delivered from space, has long influenced Earth's history. Each streak of light we see across the night sky carries the potential for both wonder and devastation, connecting the silent, cold motion of celestial bodies with the fragile, living balance of the world below. Nebulas glow with a radiant energy similar to a vast, cold flame. In the deepest reaches of space, immense, beautiful clouds of gas and dust stretch across light years, shining with the faint, delicate glow of ionized atoms. These nebulas are not hot enough to burn in the way that stars do. Their temperatures are often near absolute zero. Yet they emit light through the same fundamental quantum principles that make a fire glow. When intense ultraviolet radiation from nearby hot young stars shines on the gas, it excites the atoms, causing them to release photons in soft, specific hues of red from hydrogen, green from oxygen, and violet. The result is a flame that seems to be frozen in time, a vast tapestry of colored light that produces no heat. Within these cosmic clouds, new stars and planets are being born, shaped by the slow, patient pull of gravity and time. To gaze upon a photograph of a nebula is to witness the process of creation unfolding slowly across the ages. It is the universe breathing in color, a fire too vast and too cold to touch, painting the utter silence of space with light that has traveled for thousands of years to reach our eyes. On Titan, Saturn's largest moon, methane could burn if oxygen ever reached its atmosphere. Titan's skies are thick with an orange organic haze, and its rivers and lakes flow not with water, but with liquid methane and ethane. If a source of pure oxygen were somehow introduced into this cold, hydrocarbon-rich world, even a single spark could theoretically ignite the entire atmosphere. The planet would become a global flame, consuming itself in a single, catastrophic flash of chemistry. Scientists use this dramatic scenario to study just how fragile the balance of conditions that support life or prevent combustion can be. On Earth, the reaction between methane and oxygen is familiar. It powers our gas stoves and furnaces. But on Titan, this reaction exists only as a cold, dormant potential. The idea of an entire world that could ignite if just one wrong element appeared reveals how specific and delicate the ingredients for planetary stability truly are. In the deep, frozen silence of Titan's methane plains lies a sleeping, potential fire. Proof that combustion is not merely an act of destruction, but a possibility, patiently waiting for the right breath of air. Fire from atmospheric re-entry heats spacecraft surfaces until they glow. When a spacecraft returns to Earth, it enters the upper atmosphere at a tremendous speed, thousands of kilometers per hour. This speed violently compresses the air in front of it, generating so much friction and pressure that the gas heats up into a glowing plasma. Temperatures around the spacecraft can soar high enough to make its protective shielding glow white-hot, creating a fiery envelope around the vehicle. The brilliant streak of light we see in the sky during re-entry is not the spacecraft itself burning, but rather this envelope of superheated air radiating its intense energy. To survive this inferno, spacecraft are equipped with advanced heat shields, often made of ablative materials that are designed to absorb and shed this intense heat, layer by layer, carrying it away from the vehicle and its occupants. The process mirrors that of a natural meteor, but it is controlled and deliberate, a careful negotiation between human engineering and the raw, fundamental power of physics. Each fiery descent is a kind of rebirth, a plunge through light that recalls the earliest sparks of creation, where motion itself becomes fire, and the sky folds open to welcome its travelers home. The plasma arcs in lightning resemble miniature solar flares. Every single lightning bolt is a brief but incredibly powerful surge of plasma, the very same state of matter that fills the sun's atmosphere. In that split-second flash, the air in the bolt's path is transformed into an electrically charged gas, glowing intensely as electrons are ripped from their atoms and leap between them. The temperature within the bolt can exceed that of the solar surface, and the energy it releases is enough to power cities, if only for a few moments. The beautiful, branching patterns that lightning often forms in the sky visually mirror the massive magnetic loops that shape solar flares on the sun, just on a colossal scale. Both phenomena are born from powerful electric and magnetic fields snapping under immense stress, releasing their stored energy in sudden, brilliant bursts of light. Observing a lightning strike up close offers a glimpse into the very same forces that rage across the surfaces of stars. Each flash is a powerful reminder that the fire of the heavens is not entirely distant. It lives and breathes within our own sky, pulsing between the clouds and the earth, like the vast electric breath of a living cosmos. Every flame on earth is a faint, chemical echo of the stars that forged its atoms. The carbon, the hydrogen, and the oxygen that feed every fire we light were themselves born billions of years ago in the nuclear furnaces at the cores of ancient, massive stars. When those stars reached the end of their lives and exploded as supernovas, they scattered these newly created elements throughout space, seeding the vast clouds of gas and dust that would one day coalesce to become our Earth, our atmosphere, and our bodies. Each spark we light today, whether in a candle or a campfire, is a continuation of that original cosmic fusion. It is the same fundamental transformation of matter into energy that began in the heart of the cosmos. A simple, flickering candle flame connects us directly to the life cycles of suns that vanished long before our planet even formed. Its gentle light carries the distant, ancient memory of explosions beyond all imagination, condensed into a warmth that we can hold in our hands. Fire is not merely a human discovery, it is a cosmic inheritance. Every flicker in the dark is the universe remembering itself, burning quietly in miniature and whispering the long story of its own beginning. As the light of the last flame begins to fade, the mind starts to soften. You have wandered this evening through the secret chemistry of fire, through sparks that whisper the language of the distant stars and embers that carry the ancient memory of creation itself. Each flicker has been a gentle reminder that what burns is never truly lost. It only changes its form, finding new and different ways to glow. Fire is a teacher of transformation. It shows us how energy moves, how stillness can hide intense motion, and how every single atom carries a story that is older than time. The very same forces that warm the edge of a candle's wick are those that ignite the hearts of suns, shaping everything we see and everything we are. To watch a fire is to witness the universe remembering itself, transforming endlessly from one shape of light into another. Now, the warmth begins to settle deep within. The body grows heavy, the breath deepens, and your thoughts slow to match an ember's quiet, steady rhythm. The room around you fades into the softness of shadow, while the echo of the fire continues somewhere far away in the hush that exists between worlds. Let yourself drift with it. Feel the profound calm that follows every spark. The stillness that now holds the memory of the flame. Somewhere far beyond your sight, the stars are still burning, their ancient, steady light flowing through the dark. It greets you, even now, gently, like a final, tired spark finding its way home. If you happen to still be awake, you can go ahead and watch the next video now. But if your eyes are already closing, just let the glow fade completely and rest in the deep, profound warmth of the quiet that remains. The fire is still out there, watching over everything, and it will be waiting for you when you wake. Good night.